If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The hidden structure of the universe. Imagine gazing into the depths of the night sky. Each pinpoint of light a star, a galaxy, or even a cluster of galaxies. While breathtaking, this view barely scratches the surface of what truly binds the cosmos. Beneath the surface of visible light lies an intricate, hidden architecture, an immense network of filaments, voids, and nodes known as the cosmic web. This web, stretching across billions of light years, is the scaffolding upon which the universe builds its grand structures, including galaxies, galaxy clusters, and superclusters. To understand the cosmic web, we must first grasp the scale of the universe. Our Milky Way, with its hundreds of billions of stars, is merely one galaxy among trillions. These galaxies do not float randomly in space. Instead, they align along massive, interconnected filaments of dark matter and gas. The result is a vast, three-dimensional lattice, reminiscent of a spider's web or a neural network. Between these filaments lie enormous voids, regions of the universe, so empty that they defy comprehension. But what exactly forms this cosmic web, and why does it exist? To answer that, we must journey back to the very beginning, the Big Bang. Approximately 13.8 billion years ago, the universe was a hot, dense soup of particles. As it expanded and cooled, quantum fluctuations, tiny variations in density, left their imprint on the fabric of space-time. Over millions of years, these fluctuations grew under the influence of gravity, creating regions of higher and lower density. The denser regions became the filaments and nodes of the cosmic web, while the less dense regions formed the voids. Dark matter, an invisible substance that makes up approximately 85% of the universe's mass, plays a pivotal role in this structure. Unlike ordinary matter, dark matter does not interact with light or electromagnetic forces, making it invisible to telescopes. However, its gravitational influence is undeniable. Clumps of dark matter attract regular matter, pulling it into the filaments and nodes of the cosmic web. Without dark matter, the universe as we know it would lack the structure necessary for galaxies and life itself to form. Recent advancements in technology have allowed scientists to map this hidden web with astonishing precision. One of the key methods involves observing the light from distant galaxies and quasars. As this light travels through space, it passes through the cosmic web's filaments, revealing their presence through subtle distortions. Another technique, known as gravitational lensing, uses the warping of light by massive structures to trace the web's shape. These methods have confirmed what simulations have long predicted. The universe is far more connected than it appears. Perhaps the most intriguing aspect of the cosmic web is its duality, a balance between chaos and order. On one hand, the web appears random, with filaments twisting and turning in unpredictable ways. On the other hand, its structure follows the principles of physics, creating a harmonious balance between gravity and expansion. This balance has profound implications for the universe's evolution, influencing everything from the formation of galaxies to the behavior of dark energy. In this hidden structure lies a profound story of the universe's journey from simplicity to complexity. The cosmic web not only governs the distribution of matter, but also provides a framework for understanding our place in the cosmos. The nodes, where filaments intersect, are the birthplaces of galaxy clusters, while the filaments themselves act as highways for the movement of gas and stars. Meanwhile, the vast voids remind us of the emptiness that pervades most of the universe, a stark contrast to the dense regions of activity. As we continue to unravel the mysteries of the cosmic web, new questions emerge. How do galaxies interact with the web that supports them? What role does dark energy play in shaping the web's evolution? And most tantalizingly, could the structure of the web itself hold clues to the universe's ultimate fate? One thing is certain: the cosmic web is not just a passive backdrop to the universe's story. It is an active participant, shaping and being shaped by the forces that govern existence. The filaments of dark matter. Beneath the visible glow of galaxies lies the unseen backbone of the universe. The filaments of dark matter. These enigmatic strands, vast and interconnected, serve as the scaffolding upon which the universe's luminous structures are built. But what are these filaments made of? And how do they orchestrate the formation of galaxies and clusters? To begin understanding, we must delve into the nature of dark matter itself. Unlike ordinary matter, which interacts with light and can be observed directly, dark matter is completely invisible. It neither emits nor absorbs electromagnetic radiation, leaving no direct trace for telescopes to detect. However, its gravitational effects are undeniable. This invisible substance outnumbers ordinary matter by a ratio of approximately 5-to-1, making it the dominant form of matter in the universe. Without dark matter, the cosmic web, and consequently the galaxies within it, could not exist. The filaments of dark matter began forming in the early universe. After the Big Bang, slight variations in density, amplified by the relentless pull of gravity, caused regions of higher density to attract surrounding material. Over time, these regions grew into elongated structures, forming the filaments that now stretch across the cosmos. These filaments are not merely lines in space. They are immense rivers of dark matter, spanning tens to hundreds of millions of light years. Their gravitational influence acts like a cosmic magnet, drawing ordinary matter into their folds. Hydrogen and helium gas, the building blocks of stars, stream along these filaments, pooling in the densest regions where galaxies are born. In this way, the filaments of dark matter are both the architects and lifeblood of the universe's structure. To visualize these filaments, scientists rely on both simulations and indirect observations. Advanced cosmological simulations, like the Millennium Simulation, model the evolution of the universe by incorporating the effects of dark matter. These simulations reveal a web-like structure, with filaments crisscrossing and intersecting at dense nodes. The resemblance to neural networks or biological systems is striking, hinting at universal patterns of organization. Observing the real cosmic web is more challenging. One method involves studying the gravitational lensing of light. As light from distant galaxies passes through a filament of dark matter, its path is subtly bent by the filament's gravitational pull. By analyzing these distortions, astronomers can map the otherwise invisible dark matter. Another approach uses the distribution of galaxies themselves. Since galaxies trace the underlying structure of dark matter, their positions provide clues to the location of the filaments. One of the most fascinating discoveries about dark matter filaments is their ability to connect galaxies and clusters across vast distances. These connections act as intergalactic highways, transporting gas and even galaxies between clusters. In fact, the material that fuels star formation within galaxies often originates in these filaments, funneled inward by gravitational forces. The dynamics within the filaments are equally intriguing. At their intersections, where multiple filaments converge, gravitational forces are particularly intense, leading to the formation of galaxy clusters and superclusters. These nodes are some of the universe's most energetic regions, where collisions between galaxies and the heating of gas produce spectacular phenomena. Meanwhile, along the filaments themselves, streams of matter move steadily, like rivers feeding into great lakes. Despite their importance, many aspects of dark matter filaments remain shrouded in mystery. For instance, the exact composition of dark matter is still unknown. Leading candidates include weakly interacting massive particles, WIMPs, and axions, but neither has been definitively detected. Understanding the true nature of dark matter could unlock deeper insights into the structure and behavior of the cosmic web. The filaments also offer tantalizing clues about the interplay between dark matter and ordinary matter. Observations suggest that the filaments are not purely composed of dark matter, but are laced with ordinary gas and plasma. These components interact in complex ways, influencing the rate of star formation and the growth of galaxies. For example, the turbulence within a filament can trigger the collapse of gas clouds, igniting the birth of stars. Moreover, the filaments may hold the key to understanding dark energy, the mysterious force driving the universe's accelerated expansion. As the cosmic web evolves, the influence of dark energy becomes more apparent, stretching the filaments and reshaping their structure. By studying these changes, scientists hope to learn more about the nature of dark energy and its impact on the universe's fate. Beyond their scientific significance, the filaments of dark matter also invite philosophical reflection. They remind us that the visible universe, stars, galaxies, and all the wonders we can see, is only a fraction of what exists. The true structure of the cosmos is woven from the unseen, a humbling reminder of how much remains to be discovered. As our understanding of dark matter filaments deepens, so too does our appreciation for their role in shaping the universe. They are the silent architects of the cosmos, pulling together the threads of existence and weaving them into the vast tapestry of the cosmic web. Every galaxy, including our own, owes its existence to these hidden strands. And as we look deeper into their mysteries, we inch closer to answering some of the universe's most profound questions. Voids, the universe's empty heartlands. Amid the grandeur of galaxies and the cosmic web's intricate filaments lies a paradoxical enigma: the voids. These immense regions, nearly devoid of matter, punctuate the universe's structure like vast, silent deserts. At first glance, they might seem like the forgotten spaces of the cosmos, but their existence and behavior hold profound implications for understanding the universe's past, present, and future. Voids are not simply empty. They are the most expansive structures in the universe, often spanning hundreds of millions of light years. These regions are defined by their extreme lack of galaxies, stars, and even dark matter. While the filaments of the cosmic web are densely packed with material, voids represent the antithesis, places where matter has flowed outward over billions of years due to the gravitational pull of denser regions nearby. The story of voids begins in the aftermath of the Big Bang. As the early universe expanded, tiny fluctuations in density began to grow. Gravity caused matter to clump together, forming the seeds of what would become galaxies, stars, and the filaments of the cosmic web. In contrast, the regions with lower density lost their material to these gravitational hubs, becoming emptier over time. This natural sorting process left behind the vast voids we see today. To the naked eye, voids might seem irrelevant. After all, what could regions with so little matter possibly contribute to the grand narrative of the cosmos? Yet, these seemingly barren expanses play a crucial role in the evolution of the universe. For one, voids are critical to understanding the universe's large-scale structure. By studying their size, shape, and distribution, scientists can infer how the universe has expanded over time and gain insights into the behavior of dark energy. Voids are not completely devoid of material. They contain tenuous gas, sparse galaxies, and traces of dark matter, though at much lower densities than surrounding regions. These residual materials provide a unique laboratory for studying phenomena that are harder to observe in denser environments. For example, the intergalactic medium, the diffuse gas that permeates the space between galaxies, is more easily observed in voids, where it is not overshadowed by brighter objects. One of the most surprising findings about voids is their near-perfect spherical shape. While filaments twist and tangle in complex ways, voids tend to expand uniformly. This characteristic arises from their relatively low gravitational forces, which allow them to grow without significant interference from surrounding structures. Their shape provides valuable clues about the physics governing the universe's expansion. Voids also serve as cosmic amplifiers for the effects of dark energy. As the universe expands, dark energy pushes voids to grow larger, making them excellent test beds for studying this mysterious force. By observing how voids evolve over time, astronomers can refine their understanding of dark energy's influence on the universe's accelerating expansion. The galaxies that do inhabit voids are equally fascinating. Known as void galaxies, these isolated systems differ from their counterparts in denser environments. Without the gravitational tug-of-war common in galaxy clusters, void galaxies evolve more slowly and exhibit unique characteristics. For instance, they often have lower rates of star formation and retain more of their primordial gas. Studying these galaxies provides insights into how isolation impacts the development of galaxies. Another intriguing phenomenon associated with voids is the cosmic flow. This term describes the movement of galaxies and matter away from voids and toward the denser regions of the cosmic web. These flows contribute to the universe's overall structure, carving out the voids while simultaneously feeding the filaments. The interplay between these movements underscores the dynamic nature of the cosmic web, even in its emptiest regions. Despite their apparent simplicity, voids present a host of unanswered questions. For example, how do voids interact with dark matter and dark energy? What role do they play in shaping the cosmic web? And could voids hold clues about the universe's ultimate fate? Some theories even suggest that voids could be the best places to test alternative models of gravity, as their low-density environments amplify subtle deviations from standard predictions. Voids also challenge our understanding of what constitutes emptiness. While they are often described as barren, voids are teeming with subtle activity. The faint glow of intergalactic gas, the gentle pull of dark matter, and the slow drift of galaxies remind us that even the emptiest parts of the universe are far from static. Philosophically, voids invite us to reflect on the balance between presence and absence in the cosmos. They are a testament to the universe's duality, where creation and emptiness coexist. While the filaments of the cosmic web represent structure and growth, the voids embody the space necessary for these structures to exist. Without voids, the cosmic web would lack its defining contrast, and the universe as we know it would be fundamentally different. The study of voids is still in its infancy, but their significance is becoming increasingly clear. As astronomers refine their techniques and simulations grow more sophisticated, the role of voids in shaping the universe will likely come into sharper focus. These vast, quiet expanses may hold answers to some of the most profound questions in cosmology, from the nature of dark energy to the universe's ultimate destiny. The next time we look at the night sky, it's worth remembering that for every luminous galaxy we see, there is an ocean of darkness surrounding it. These voids, though silent and unseen, are as much a part of the universe as the stars themselves, a reminder that sometimes it is the emptiest spaces that speak the loudest. Galactic highways, the filamentary roads of the cosmos. Beneath the dazzling tapestry of galaxies lies a network of highways that interconnect the universe, the filaments of the cosmic web. These colossal threads, composed of dark matter, gas, and galaxies, act as the pathways of the cosmos, guiding the movement of material and energy across unimaginable distances. They are not merely inert structures. They are dynamic conduits of cosmic evolution, shaping the fate of galaxies and clusters alike. The concept of filaments as galactic highways stems from their unique role in the large-scale structure of the universe. These filaments are the bridges between galaxy clusters, spanning millions of light years and forming a framework that connects the densest regions of the cosmos. Along these threads, galaxies and intergalactic gas flow, pulled by the inexorable force of gravity. This flow is not random, but follows the patterns dictated by the cosmic web, creating a vast, interlinked network of activity. Understanding how these highways formed requires a step back in time to the universe's infancy. In the chaotic moments after the Big Bang, quantum fluctuations created tiny differences in density. Over billions of years, gravity amplified these differences, pulling matter into elongated structures that would become the filaments of the cosmic web. These filaments are now the veins of the universe, transporting material from sparse voids to the dense nodes where galaxy clusters thrive. The movement of matter along these filaments is one of their most remarkable features. Like rivers feeding into oceans, the filaments funnel gas and galaxies into larger structures, fueling their growth. This process is particularly vital for galaxy clusters, which rely on the steady inflow of material to maintain their immense size and activity. Without these highways, the universe's largest structures would stagnate, unable to sustain the dynamic processes that define them. But these galactic highways are not uniform. Each filament has unique properties, influenced by its density, length, and the type of matter it contains. Some filaments are rich in gas, serving as nurseries for new stars and galaxies. Others are dominated by dark matter, exerting a gravitational pull that directs the movement of visible matter. Together, they create a complex web that is as diverse as it is interconnected. To observe these filaments, astronomers rely on advanced techniques and instruments. One key method involves studying the distribution of galaxies, which tend to align along the filaments. By mapping the positions of millions of galaxies, scientists can trace the outline of the cosmic web. Another approach uses the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars caused by intervening hydrogen gas. This gas, distributed along the filaments, provides a subtle but powerful way to map their structure. Gravitational lensing, a phenomenon where massive objects bend the light of more distant sources, offers yet another window into these highways. By measuring the distortions caused by dark matter within filaments, astronomers can create detailed maps of their invisible structure. These observations confirm what simulations have long predicted. The cosmic web is a vast network, with filaments connecting galaxies like neural pathways in a cosmic brain. The influence of these highways extends beyond simple connectivity. They play a crucial role in shaping the galaxies that traverse them. For instance, galaxies moving along a filament often encounter streams of gas that can fuel star formation. At the same time, interactions between galaxies within a filament can trigger mergers, altering their structure and activity. In some cases, the gravitational forces within a filament can strip a galaxy of its gas, halting star formation and transforming it into a red and dead system. Filaments also act as stages for some of the universe's most dramatic events. When two galaxy clusters merge at the intersection of filaments, the collision generates enormous amounts of energy, producing shocks and turbulence that can be observed in X-rays. These collisions are among the most powerful events in the universe, rivaled only by the Big Bang itself. Despite their importance, filaments remain one of the least understood components of the cosmic web. Many questions linger. How do the properties of filaments vary across the universe? What role do magnetic fields play within them? How does the interplay between dark matter and ordinary matter shape their evolution? These questions drive ongoing research as astronomers and physicists work to unravel the complexities of these galactic highways. The relationship between filaments and voids is another area of intrigue. While filaments are the highways of the cosmos, voids are the spaces between them, vast regions where matter is sparse. Yet even these empty spaces are influenced by the presence of filaments, which help define their boundaries. This interplay between emptiness and structure is a reminder of the cosmic web's intricate balance, a system where opposites coexist and shape one another. In addition to their scientific significance, the filaments of the cosmic web inspire awe and reflection. They remind us that the universe is not a collection of isolated objects, but a deeply interconnected system. Every galaxy, including our Milky Way, is part of this grand network, shaped by forces that stretch across billions of light years. These highways also challenge our understanding of movement and time. The journeys of galaxies along filaments are measured not in years or centuries, but in cosmic epochs. A single trip from one end of a filament to another could take hundreds of millions of years. Yet, these movements are essential to the universe's evolution, shaping the distribution of matter and the formation of new structures. As our understanding of the cosmic web deepens, the role of filaments becomes increasingly clear. They are not merely the scaffolding of the universe, but active participants in its growth and transformation. From fueling star formation to orchestrating galaxy mergers, these highways are the lifelines of the cosmos, ensuring its continual dynamism. The next time we look at the stars, it is worth imagining the invisible threads connecting them. These filaments, though unseen, are the roads upon which the universe travels, a reminder that even in the vastness of space, everything is connected. Mapping the invisible. Techniques of discovery. How do you map the invisible? The cosmic web, with its vast filaments of dark matter and gas, lies hidden from our direct view, shrouded in the mysteries of the unseen. Yet, through innovative techniques and technological advancements, scientists have developed remarkable tools to reveal this intricate structure. Mapping the cosmic web is more than just an observational feat. It's a testament to human ingenuity and our relentless curiosity about the universe. The challenge of observing the cosmic web begins with its primary component, dark matter. Unlike ordinary matter, dark matter does not emit, reflect, or absorb light, making it undetectable through traditional telescopes. Its presence is known only through its gravitational effects, which influence the motion of galaxies and the bending of light. To uncover the web's hidden framework, astronomers have turned to indirect methods, leveraging the interplay between dark matter, ordinary matter, and light. One of the most effective techniques for mapping the cosmic web is galaxy surveys, which trace the distribution of luminous matter across the universe. Galaxies are not randomly scattered. They cluster along the filaments of the cosmic web. By cataloging the positions of millions of galaxies, scientists can outline the web structure, much like sketching a map by plotting the locations of cities and roads. Projects like the Sloan Digital Sky Survey (SDSS) have revolutionized this approach, producing detailed, three-dimensional maps of the universe that reveal its large-scale organization. Another groundbreaking method is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from a distant galaxy or quasar passes through a region of dark matter, the dark matter's gravitational field bends the light, distorting the image of the background object. These distortions, known as weak lensing, are subtle but measurable. By analyzing these distortions across vast regions of the sky, astronomers can infer the distribution of dark matter and, consequently, the structure of the cosmic web. Gravitational lensing has provided some of the most compelling evidence for the existence and arrangement of the cosmic web. For example, the Dark Energy Survey (DES) has used lensing data to create detailed maps of dark matter filaments, revealing their connection to galaxy clusters and voids. These maps not only confirm theoretical predictions, but also offer new insights into the relationship between dark matter, ordinary matter, and cosmic evolution. For the gaseous components of the web, astronomers rely on the Lyman alpha forest, a tool as poetic as it is powerful. The Lyman alpha forest refers to a series of absorption lines in the spectra of light from distant quasars. As this light passes through the intergalactic medium, composed mainly of hydrogen gas, it is absorbed at specific wavelengths, creating a pattern that reflects the density and distribution of the gas along the line of sight. By analyzing these absorption patterns, scientists can map the gaseous filaments of the cosmic web with remarkable precision. This technique has been particularly effective in studying the regions of the cosmic web far from galaxies, where the gas is too diffuse to emit visible light. Observations with telescopes like the Keck Observatory and the Very Large Telescope (VLT) have revealed the intricate networks of gas that connect galaxies and feed star formation within them. These studies provide a window into the cosmic web's role as a conduit for matter and energy. The cosmic microwave background (CMB), the faint afterglow of the Big Bang, also plays a role in mapping the cosmic web. Tiny temperature fluctuations in the CMB, caused by variations in the density of matter in the early universe, serve as a blueprint for the web's initial formation. By comparing these fluctuations with the current distribution of galaxies and dark matter, scientists can trace the evolution of the cosmic web over billions of years. Computer simulations are another essential tool in this endeavor. Advanced cosmological simulations, such as the Illustris and Eagle projects, model the behavior of dark matter, gas, and galaxies under the influence of gravity and other forces. These simulations allow scientists to recreate the formation and evolution of the cosmic web in unprecedented detail, providing a theoretical framework to interpret observational data. By comparing simulation results with real-world observations, astronomers can test and refine their understanding of the universe. The role of artificial intelligence, AI, in mapping the cosmic web is growing rapidly. Machine learning algorithms can analyze vast datasets from galaxy surveys, gravitational lensing studies, and quasar spectra, identifying patterns and structures that might otherwise go unnoticed. AI has also been instrumental in processing the enormous volumes of data generated by modern telescopes, enabling scientists to map the cosmic web more efficiently and accurately. Despite these advances, challenges remain. Observing the cosmic web requires extremely sensitive instruments and careful analysis to distinguish its faint signals from background noise. Moreover, the vast scales involved, spanning billions of light years, demand sophisticated techniques to stitch together data from multiple sources and perspectives. Each new discovery raises new questions, driving the development of even more powerful tools and methods. One of the most exciting frontiers in cosmic web mapping is the use of multi-wavelength observations, combining data from X-ray, optical, infrared, and radio telescopes. This approach provides a more comprehensive view of the web, revealing the interactions between its different components. For example, X-ray observations of hot gas and galaxy clusters complement optical surveys of galaxies and gravitational lensing maps of dark matter, painting a fuller picture of the web's complexity. Mapping the cosmic web is more than a technical achievement. It is a journey into the heart of the universe's structure and history. Each filament traced, each void measured, brings us closer to understanding the forces that shape the cosmos. The web is not just a backdrop for galaxies. It is the stage upon which the drama of cosmic evolution unfolds. As we continue to refine our techniques and expand our observational capabilities, the cosmic web will reveal even more of its secrets. Its intricate design, born of quantum fluctuations and sculpted by gravity, is a reminder of the universe's extraordinary capacity for organization and complexity. From the faint glow of distant quasars to the subtle distortions of light, every observation is a thread in the grand tapestry of the cosmos. The birthplaces of stars and galaxies. Within the vast and intricate cosmic web, there are regions where matter converges, collapsing under gravity's relentless pull. These are the birthplaces of stars and galaxies, the bustling hubs of cosmic activity. These dense nodes and filaments are not only the foundations of the universe's largest structures, but also the cradles where light emerges, illuminating the darkness of space. How do such colossal structures give rise to stars and galaxies? And what processes govern their formation? The story begins with the primordial gas that permeates the universe, mainly hydrogen and helium, the simplest and most abundant elements created during the Big Bang. This gas flows along the cosmic web's filaments, pulled by the gravitational influence of dark matter. As the gas collects at the intersections of filaments, it creates dense regions known as nodes, which act as gravitational wells. Within these wells, galaxies and stars begin their journey of formation. The filaments themselves play a critical role in this process. They act as cosmic rivers, channeling gas into the nodes where it accumulates. Without this steady supply, the star formation process would falter, as galaxies require a continuous influx of material to sustain their growth. The density of the gas within the filaments is not uniform. Pockets of higher density form along the way, creating smaller gravitational wells. These are the sites where smaller galaxies or even star clusters can emerge. The transformation of gas into stars is a delicate dance governed by the interplay of gravity, temperature, and turbulence. When a pocket of gas within a filament or node becomes dense enough, its own gravity causes it to collapse. As the gas collapses, it heats up, eventually reaching temperatures high enough to ignite nuclear fusion, the process that powers stars. The result is the birth of a star, its light marking a new beacon in the cosmic web. This process does not occur in isolation. Stars tend to form in clusters, as the collapse of one gas cloud often triggers the collapse of nearby clouds. These star-forming regions are some of the most dynamic and beautiful parts of the universe, filled with glowing nebulae and energetic phenomena like stellar winds and supernova explosions. The energy released by these events can further shape the surrounding environment, compressing gas clouds and igniting more star formation in a cascading effect. Galaxies, in turn, are the homes of these stars. Their formation begins when gas and dark matter within a node or along a filament coalesce into a rotating disk. Over time, this disk grows as more gas flows in, fueling the birth of new stars. The interplay between the galaxy's gravitational forces and the inflow of material determines its size, shape, and structure. Spiral galaxies, like the Milky Way, often form in regions with steady, moderate inflows of gas, while elliptical galaxies may result from more chaotic interactions, such as galaxy mergers. Interestingly, the location of a galaxy within the cosmic web strongly influences its evolution. Galaxies in the dense nodes of the web, where filaments intersect, are more likely to interact with other galaxies. These interactions can range from gentle gravitational tugs to full-fledged collisions, which can trigger bursts of star formation or even transform a galaxy's shape. Conversely, galaxies located along the filaments or in more isolated regions tend to evolve more slowly, with less external influence. The role of feedback processes in shaping star and galaxy formation cannot be overstated. As stars form, they emit intense radiation and winds that can blow away surrounding gas, halting further star formation in their immediate vicinity. Similarly, supermassive black holes at the centers of galaxies can emit powerful jets and winds, heating the surrounding gas and preventing it from collapsing into new stars. These feedback mechanisms create a delicate balance, regulating the rate of star formation and ensuring that galaxies do not consume all their gas too quickly. Observing these processes in action requires advanced technology and techniques. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope (JWST) have provided stunning images of star-forming regions, revealing the intricate interplay of gas, dust, and gravity. Infrared observations, in particular, are crucial for studying these regions, as they can penetrate the thick clouds of gas and dust that often obscure the view in visible light. One of the most exciting frontiers in the study of star and galaxy formation is the use of simulations. By modeling the behavior of gas, dark matter, and radiation under the influence of gravity, scientists can recreate the conditions that lead to the formation of stars and galaxies. These simulations, such as the Illustris and Eagle projects, have provided valuable insights into the role of the cosmic web in shaping the universe's largest and smallest structures. Despite these advancements, many questions remain. For instance, why do some galaxies form stars at extraordinary rates, while others appear to be quenched with little to no star formation? What determines the specific structures of galaxies, from spirals to irregular shapes? And how do the properties of the cosmic web, such as the density and orientation of filaments, influence these outcomes? The answers to these questions lie in the cosmic web itself. Its filaments and nodes are not just passive structures. They actively shape the flow of material, the interactions between galaxies, and the conditions for star formation. The web's architecture provides the framework for the universe's story, guiding the evolution of its luminous inhabitants. Reflecting on the birthplaces of stars and galaxies reminds us of the interconnectedness of the cosmos. Every star that lights up the night sky, every galaxy that graces the universe's vast expanse, owes its existence to the invisible threads of the cosmic web. These structures are the wombs of creation, nurturing the forces that bring light and complexity into the universe. As we continue to explore the cosmic web, the story of star and galaxy formation will come into sharper focus. Each discovery brings us closer to understanding the intricate processes that have shaped the universe for billions of years. From the gas clouds that collapse into stars to the galaxies that grow along filaments, the cosmic web is a testament to the universe's capacity for creativity and order. Have you ever looked at the sky and felt the desire to understand your place in the universe? On Beyond the Stars, every video is a window to infinity, a journey to connect you with the mystery and beauty of the cosmos. Subscribing to the channel is more than clicking a button. It's joining a movement to spread knowledge and inspire others to look at the stars with hope and curiosity. Be the light that guides others to discover the wonders of the universe. Subscribe, and let's explore the unknown together. The role of gravity in cosmic sculpting. Gravity is the silent architect of the cosmos, an omnipresent force that has shaped the universe from its earliest moments. From the tiniest quantum fluctuations in the aftermath of the Big Bang to the sprawling structures of the cosmic web, gravity is the unseen hand guiding the formation of stars, galaxies, and the vast network of filaments that crisscross the universe. How does this fundamental force sculpt the intricate patterns of the cosmic web? And what role does it play in maintaining the universe's delicate balance? To understand gravity's influence, we must first consider its universal reach. Unlike other fundamental forces, gravity acts across infinite distances, binding together the universe's disparate components. Its strength diminishes with distance, but its cumulative effect is profound, especially on large scales. Over billions of years, gravity has transformed an initially uniform universe into the complex, hierarchical structures we observe today. The story of cosmic sculpting begins shortly after the Big Bang. The early universe was a near-homogeneous soup of particles and energy, punctuated by tiny density fluctuations. These fluctuations, imprinted by quantum mechanics, were minuscule, mere 1 part in a million variations in density. Yet, they provided the seeds for all future structure. Gravity amplified these differences, pulling matter from less dense regions into denser ones, setting the stage for the formation of the cosmic web. As the universe expanded, gravity worked tirelessly, pulling material into elongated structures that became the filaments of the cosmic web. These filaments are not static. They are dynamic entities, continually shaped and reshaped by gravity. Streams of gas and dark matter flow along the filaments, funneling material into nodes where galaxy clusters form. This process, known as gravitational collapse, is the driving force behind the web's evolution. The cosmic web's hierarchical nature, filaments feeding nodes, nodes forming clusters, and clusters interacting, can be directly traced to gravity's organizing principle. Smaller structures like galaxies and star clusters form first, while larger structures, such as galaxy clusters and superclusters, emerge later as gravity continues to pull smaller entities together. This phenomenon, known as bottom-up structure formation, reflects the universe's constant balancing act between gravity's pull and the expansion of space. Dark matter, the enigmatic substance that makes up most of the universe's mass, plays a pivotal role in gravity's sculpting process. Although dark matter is invisible, its gravitational influence is immense. Clumps of dark matter act as anchors, pulling ordinary matter into the web's filaments and nodes. Without dark matter, gravity would lack the scaffolding needed to create the large-scale structures we see today. Simulations of the universe's evolution, which incorporate dark matter's gravitational effects, have consistently reproduced the observed structure of the cosmic web, confirming its central role. Within the web, gravity's influence varies depending on the environment. In dense regions like galaxy clusters, gravity's pull is intense, leading to frequent interactions and mergers between galaxies. These interactions can trigger bursts of star formation, disrupt galactic structures, and even fuel supermassive black holes, resulting in the emission of powerful jets and radiation. In contrast, in less dense regions, such as filaments and voids, gravity's influence is more subtle, allowing galaxies to evolve more gently. The interaction between gravity and the universe's expansion adds another layer of complexity. The universe has been expanding since the Big Bang, a process that counteracts gravity's tendency to pull matter together. Early in the universe's history, gravity dominated, allowing structures to form and grow. However, as the universe expanded, the influence of a mysterious force known as dark energy began to accelerate this expansion, pushing matter apart and slowing the growth of structures. This cosmic tug-of-war between gravity and dark energy shapes the evolution of the cosmic web and determines its ultimate fate. Observations of gravitational effects provide crucial insights into the web's structure. One of the most striking phenomena is gravitational lensing, where massive objects like galaxy clusters bend the light from background sources. This effect not only reveals the presence of dark matter, but also allows astronomers to map the distribution of matter within the web. Gravitational lensing studies have confirmed that the web's filaments are threaded with dark matter, reinforcing the idea that gravity is the web's primary architect. Gravity also governs the movement of galaxies within the web. Galaxies are not stationary. They flow along the filaments, pulled toward denser regions by gravitational forces. This movement creates a dynamic interplay between galaxies and their environment. For instance, galaxies near the edges of filaments often experience ram pressure stripping, where interactions with the hot gas in the filaments remove their outer layers of gas, halting star formation. In contrast, galaxies at the intersections of filaments, where gravitational forces are strongest, frequently collide and merge, creating massive elliptical galaxies. The role of gravity extends beyond shaping visible structures. It also influences the behavior of intergalactic gas. The gravitational pull of filaments and nodes compresses this gas, heating it to extreme temperatures and causing it to emit X-rays. Observations of this hot gas provide additional clues about the distribution of matter in the web. Moreover, This gas serves as the raw material for future star formation, linking gravity's sculpting role to the birth of stars and galaxies. As powerful as gravity is, it is not omnipotent. The accelerating expansion of the universe driven by dark energy poses a challenge to gravity's dominance. In the distant future, dark energy may stretch the web's filaments and disperse its nodes, rendering the universe a vast, sparsely populated expanse. Alternatively, if dark energy's behavior changes over time, gravity could once again assert its influence, leading to a contraction of the web structures. The study of gravity's role in cosmic sculpting is a testament to humanity's ability to understand the forces shaping our universe. Through a combination of observations, simulations, and theoretical models, scientists have uncovered the intricate relationship between gravity, dark matter, and the cosmic web. Yet, as with all great scientific endeavors, each discovery raises new questions. How does gravity interact with dark energy on the largest scales? What role do gravitational waves play in shaping the web? And could there be undiscovered forces influencing the web structure? Gravity's sculpting of the cosmic web is not merely a mechanical process. It is a profound narrative of order emerging from chaos. From the delicate balance of forces that allowed galaxies to form to the intricate patterns of the web itself, gravity has created a universe that is as beautiful as it is complex. Every star, every galaxy, and every filament is a testament to gravity's creative power, a reminder that even the smallest forces can shape the grandest structures. Cosmic evolution, from the Big Bang to the present. The universe's story is one of transformation, a tale that begins with a searing burst of energy and evolves into the vast, intricate cosmos we observe today. The cosmic web, with its sprawling filaments and massive voids, serves as the framework for this narrative, tracing the evolution of matter and structure across billions of years. How did the universe evolve from an almost uniform expanse of energy into the complex tapestry of stars, galaxies, and clusters we see now? The answer lies in the dance of cosmic forces and the passage of time. The story begins approximately 13.8 billion years ago with the Big Bang, a moment of unimaginable energy and density. In the first fractions of a second, the universe expanded exponentially in an event known as cosmic inflation, smoothing out irregularities and setting the stage for the formation of the cosmic web. During this phase, quantum fluctuations, tiny variations in the density of energy, were stretched to macroscopic scales, planting the seeds for the universe's large-scale structure. As inflation ended, the universe entered a phase of cooling and expansion, dominated by a hot plasma of particles and radiation. During this period, known as the radiation era, photons scattered off free electrons, creating a dense fog that prevented light from traveling freely. This fog lifted approximately 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, a process called recombination. This milestone allowed light to travel unimpeded, creating the cosmic microwave background, CMB, a faint glow that provides a snapshot of the universe in its infancy. The CMB reveals the universe as it was, nearly homogeneous, with tiny fluctuations in temperature corresponding to variations in density. These density variations, amplified by gravity, became the seeds of the cosmic web. Over the next few 100 million years, the universe entered the Dark Ages, a period when no stars or galaxies had yet formed. During this time, dark matter began to dominate the gravitational landscape, pulling ordinary matter into the dense regions that would become the nodes and filaments of the web. The first stars ignited approximately 100 to 200 million years after the Big Bang, ending the Dark Ages and beginning the era of reionization. The intense ultraviolet radiation from these stars ionized the surrounding hydrogen gas, making the universe transparent once more. These early stars were massive and short-lived, often ending their lives in spectacular supernovae that enriched the surrounding gas with heavier elements. These elements, forged in the hearts of stars, provided the building blocks for future generations of stars and planets. The formation of the first galaxies followed closely behind. These galaxies formed in the densest regions of the cosmic web, where the gravitational pull of dark matter had drawn in large amounts of gas. Over time, galaxies began to cluster along the filaments of the web, creating the intricate network of structure that defines the universe today. The interplay between gravity, gas dynamics, and feedback from star formation and black holes shaped these galaxies, giving rise to the diversity of forms we observe, from spirals like the Milky Way to elliptical and irregular galaxies. As the universe aged, its structures grew increasingly complex. Small galaxies merged to form larger ones, and galaxy clusters emerged at the intersections of filaments. These clusters became the universe's largest gravitationally bound structures, containing thousands of galaxies, immense reservoirs of hot gas, and dark matter. The filaments connecting these clusters continued to feed them with gas, sustaining star formation and galactic growth. The role of dark matter in this process cannot be overstated. Dark matter provided the gravitational scaffolding for the cosmic web, dictating the flow of gas and the formation of galaxies. Without dark matter, the density variations in the early universe would not have grown large enough to form the web. Simulations of the universe's evolution, such as the Millennium Simulation, have shown that dark matter's influence is critical for replicating the observed structure of the cosmos. While dark matter drove the formation of structure, another mysterious force, dark energy, began to assert itself as the universe expanded. Discovered in the late 20th century, dark energy is responsible for the universe's accelerated expansion, a phenomenon observed through the redshifts of distant galaxies. As the universe grows larger, dark energy's influence becomes more pronounced, stretching the filaments of the cosmic web and slowing the growth of structures. Today, the universe is a dynamic, ever-evolving system. Stars continue to form in galaxies, fueled by gas flowing along the filaments. At the same time, galaxies interact and merge, creating new forms and triggering bursts of star formation. In galaxy clusters, the interplay of gravity and hot gas produces dramatic phenomena, from shock waves to gravitational lensing. Meanwhile, vast voids between the filaments remind us of the universe's emptiness, a stark contrast to its regions of intense activity. As we look to the future, the cosmic web's evolution will be shaped by the interplay between gravity and dark energy. If dark energy continues to dominate, the universe's expansion will accelerate, stretching the web's filaments and isolating galaxy clusters. In this scenario, the universe could become a cold, dark expanse, with galaxies too far apart to interact. Alternatively, if dark energy's behavior changes, gravity could regain its influence, leading to a contraction of the web and possibly a dramatic end to the universe. Despite its complexity, the cosmic web's evolution is governed by a few simple principles: the pull of gravity, the push of expansion, and the flow of time. These forces have transformed the universe from a near-uniform expanse of energy into a rich tapestry of stars, galaxies, and clusters. Each filament and node is a testament to the power of these forces and the beauty of the structures they create. Reflecting on cosmic evolution reminds us of our place in this grand story. Our solar system, our planet, and even our existence are products of the processes that have shaped the cosmic web. The atoms in our bodies were forged in stars, and the galaxies we observe trace their origins to the same primordial fluctuations that gave birth to the web. In studying the cosmos, we are not merely observing distant objects. We are uncovering the history of everything. Dark energy and the web's expansion. The universe is expanding, a discovery that transformed our understanding of cosmology. Yet, this expansion is no ordinary process. It is accelerating, driven by an enigmatic force known as dark energy. While the cosmic web grows and evolves under the influence of gravity, dark energy exerts a counterforce, reshaping the web and dictating the future of the cosmos. What is this mysterious energy, and how does it affect the sprawling architecture of the cosmic web? The first clues about the universe's expansion came in the early 20th century, when astronomers observed that galaxies appear to be moving away from us, their light stretched to longer wavelengths, a phenomenon known as redshift. This discovery, coupled with Einstein's theory of general relativity, led to the realization that the universe itself is expanding, with space stretching between galaxies. For decades, scientists believed that this expansion was slowing down, as gravity worked to counteract the momentum of the Big Bang. In 1998, this assumption was upended by observations of distant type I supernovae, which revealed that the expansion of the universe is not slowing but accelerating. This unexpected finding introduced the concept of dark energy, a mysterious force thought to permeate all of space and account for roughly 68% of the universe's total energy content. Dark energy's precise nature remains one of the greatest mysteries in physics, but its effects on the cosmic web are profound. To understand dark energy's influence, we must first consider the role of gravity in shaping the cosmic web. Gravity pulls matter together, forming the dense filaments and nodes that define the web structure. This process is most effective in the early universe, when matter is relatively close together and gravity's influence is strong. Over time, however, as the universe expands, the distances between structures increase, weakening gravity's ability to pull matter together. Dark energy exacerbates this weakening. Unlike gravity, which acts locally, dark energy exerts its influence on the universe as a whole, driving the expansion of space itself. As dark energy's effects grow stronger, the rate of expansion accelerates, stretching the cosmic web and slowing the growth of its structures. In essence, dark energy works against gravity, creating a cosmic tug-of-war that shapes the evolution of the universe. This interplay between dark energy and gravity has a direct impact on the cosmic web's filaments and nodes. In the early universe, when dark energy was relatively weak, the web grew rapidly, with matter flowing into filaments and nodes to form galaxies and clusters. Today, dark energy's influence has become more pronounced, slowing the flow of matter and limiting the growth of new structures. As a result, the cosmic web is entering a more static phase, with its largest structures reaching a state of near completion. One of the most striking consequences of dark energy is its effect on the universe's largest structures, galaxy clusters. These clusters, which form at the intersections of filaments, are held together by gravity and contain thousands of galaxies. As dark energy drives the expansion of space, the distances between clusters increase, isolating them from one another. Over time, the cosmic web may fragment, with individual clusters becoming islands in an ever-expanding void. The stretching of the cosmic web also affects the filaments themselves. These vast, thread-like structures, composed of dark matter and gas, connect galaxies and clusters across the universe. As dark energy accelerates the expansion of space, the filaments become more elongated and less dense, reducing the flow of material into galaxies and clusters. This process could eventually lead to a decline in star formation, as galaxies deplete their gas supplies without replenishment from the web. Despite its dominance, dark energy's true nature remains elusive. Several hypotheses have been proposed to explain its behavior. One possibility is that dark energy is a property of space itself, described by Einstein's cosmological constant. According to this theory, as the universe expands, new space is created, and with it, more dark energy, maintaining a constant density. Another possibility is that dark energy is dynamic, evolving over time as a field known as quintessence. If true, its effects on the cosmic web could change, altering the fate of the universe. Observational evidence for dark energy comes from a variety of sources. The cosmic microwave background, CMB, the afterglow of the Big Bang, provides a snapshot of the early universe and reveals how its expansion has changed over time. Observations of large-scale structure, including galaxy surveys and gravitational lensing studies, offer insights into the distribution of matter and the influence of dark energy. Additionally, measurements of supernovae and baryon acoustic oscillations, a pattern of density fluctuations in the early universe, help constrain the properties of dark energy. The impact of dark energy on the cosmic web is not only a question of scientific interest, but also a profound reflection on the universe's ultimate fate. If dark energy continues to dominate, the universe's expansion will accelerate indefinitely, stretching the web's filaments and isolating its structures. In this scenario, galaxies within clusters may eventually exhaust their gas, halting star formation and leaving behind a cold, dark universe. Alternatively, if dark energy's behavior changes, perhaps transitioning into a stronger or weaker form. The cosmic web's evolution could take a different path. A decrease in dark energy's influence might allow gravity to regain control, leading to a contraction of the web and a possible big crunch. Conversely, an increase in dark energy strength could result in a big rip, where the expansion becomes so rapid that even the filaments of the web are torn apart. The cosmic web, with its delicate balance of forces, serves as a natural laboratory for studying dark energy. By observing how the web structure evolves over time, scientists can test theories of dark energy and refine their understanding of its properties. These studies not only illuminate the past and present of the universe, but also provide glimpses into its future. Reflecting on dark energy's role in the cosmic web invites us to consider the fragility of structure in an ever-expanding universe. The same force that has allowed galaxies and stars to form may one day render the cosmos a cold and barren expanse. Yet, in its current state, the web remains a testament to the interplay of forces that have shaped the universe, a reminder of the dynamic and ever-changing nature of the cosmos. The Milky Way's place in the cosmic web. In the vast cosmic web, our galaxy, the Milky Way, is but a single thread in a much larger tapestry. It resides within a filamentary structure of dark matter and gas, connected to its neighbors and tied to the immense gravitational forces that shape the universe. Understanding the Milky Way's position in the cosmic web is not only a matter of locating our galactic home, but also of exploring how this dynamic network influences its evolution, interactions, and even its potential future. The Milky Way belongs to a structure known as the local group, a small cluster of galaxies bound together by gravity. The local group contains over 50 galaxies, including our nearest major neighbor, the Andromeda Galaxy, and numerous smaller dwarf galaxies such as the Magellanic Clouds. Together, these galaxies inhabit a filament of the cosmic web, surrounded by vast voids and connected to larger structures like the Virgo supercluster and the Laniakea supercluster, a gravitationally bound region encompassing thousands of galaxies. At first glance, it might seem that the Milky Way and its neighbors are isolated entities, moving through space independently. However, their positions and motions are deeply influenced by the larger-scale structure of the cosmic web. Filaments of dark matter act as gravitational highways, guiding the movement of galaxies and channeling gas into their centers. The Milky Way itself likely formed at the intersection of smaller filaments, where material was funneled together to create the dense environment necessary for star and galaxy formation. The Milky Way's location within the local group and its connections to the cosmic web have shaped its evolutionary history. For example, the inflow of gas along filaments has provided the raw material for star formation over billions of years. This gas, primarily composed of hydrogen, enters the galaxy's halo, where it cools and condenses, eventually forming new stars in the Milky Way's spiral arms. Without this continuous supply of gas from the cosmic web, the galaxy would have long since exhausted its reserves. Interactions with neighboring galaxies have also played a significant role in shaping the Milky Way. The gravitational pull of the Andromeda Galaxy, for instance, influences the Milky Way's motion and will eventually result in a collision between the two galaxies in about 4.5 billion years. These types of galactic interactions, common in the cosmic web, can trigger bursts of star formation, reshape galactic structures, and even lead to the formation of new, larger galaxies. The Milky Way's position within the cosmic web is also tied to its role as a cosmic bridge. The galaxy acts as a node in the larger network, connecting smaller galaxies and satellite systems. These satellite galaxies, like the Magellanic Clouds, orbit the Milky Way and contribute to its evolution through processes such as tidal stripping, where gas and stars are pulled from the satellites and absorbed into the Milky Way. This process enriches the galaxy with new material, further fueling its growth and activity. Beyond its immediate surroundings, the Milky Way's place in the Laniakea supercluster highlights the interconnected nature of the cosmic web. This supercluster, spanning over 500 million light-years, is one of the largest known structures in the universe. It contains tens of thousands of galaxies, all moving in response to the gravitational pull of a central region called the Great Attractor, a dense cluster of galaxies and dark matter. The Milky Way and its neighbors are drawn toward this region, their motions influenced by the underlying dark matter filament that links them to the supercluster. The cosmic web also provides insights into the Milky Way's past. By studying the distribution of galaxies and the flow of material along filaments, scientists can reconstruct the history of the galaxy's formation and growth. For instance, the Milky Way likely accreted much of its mass through the merging of smaller proto-galaxies in its early history, a process driven by the gravitational forces of the web. These mergers shaped the galaxy's structure, creating its characteristic spiral arms and central bulge. One of the most intriguing aspects of the Milky Way's connection to the cosmic web is its potential future. As dark energy drives the accelerated expansion of the universe, the filaments connecting galaxies and clusters will become increasingly stretched. Over time, the local group's galaxies may become isolated from the larger cosmic web, their motions dominated solely by their mutual gravitational attraction. In this scenario, the Milky Way and Andromeda could merge to form a single, massive elliptical galaxy, while the rest of the universe drifts out of reach. Despite its relatively modest size compared to some of the universe's largest galaxies and clusters, the Milky Way's position in the cosmic web underscores its importance as a hub of activity. It is a microcosm of the larger processes that govern the universe, from the flow of gas and matter to the interactions between galaxies. Its connections to the cosmic web illustrate the dynamic and interconnected nature of the cosmos, where even the smallest threads contribute to the grand design. Exploring the Milky Way's place in the cosmic web is more than an exercise in astronomy. It is a journey into our cosmic identity. By understanding how the galaxy fits into the larger structure of the universe, we gain insights into the forces that shaped not only the Milky Way, but also the solar system and, ultimately, life on Earth. Every star that shines in the Milky Way's arms, every planet that orbits its stars, is a product of the galaxy's position and history within the cosmic web. As we continue to study the Milky Way's connections to the web, new questions emerge. How do the galaxy's interactions with its satellites and neighbors influence its evolution? What role does the flow of gas along filaments play in sustaining star formation? And how will the galaxy's position in the web change as the universe continues to expand? The answers to these questions lie at the intersection of observation and theory, where telescopes like the James Webb Space Telescope and advanced cosmological simulations provide new windows into the universe's structure. By piecing together the Milky Way's story, we deepen our understanding of the cosmic web and our place within it, a reminder that even amid the vastness of space, every thread is connected. The interplay of galaxies, mergers, and interactions. The cosmic web is not a static framework. It is alive with motion and interaction. Galaxies, the luminous nodes of this vast structure, are far from solitary. Instead, they are participants in an intricate dance, constantly interacting, colliding, and merging. These interactions shape the galaxies themselves and the cosmic web as a whole, driving the evolution of the universe's grandest structures. But what triggers these interactions, and how do they reshape the galaxies involved? Galactic interactions occur because gravity binds galaxies to one another, even as the universe expands. While the space between galaxies grows, local groups and clusters remain gravitationally connected. Within these clusters and along the filaments of the cosmic web, galaxies often pass close to one another, their gravitational fields overlapping and creating a cascade of effects. The simplest form of interaction is a gravitational encounter, where two galaxies pass near one another without directly merging. These encounters can stretch and distort the galaxies, creating spectacular tidal tails, streams of stars and gas flung outward by gravitational forces. Such tails are visible in systems like the Antennae galaxies, where two interacting galaxies have produced sweeping arcs of stars. These structures not only highlight the dynamic nature of galaxies, but also serve as sites for intense star formation, as the interactions compress gas clouds and ignite stellar nurseries. More dramatic interactions involve galactic mergers, where two or more galaxies collide and combine into a single, larger system. Mergers are a common and essential part of galactic evolution, particularly in dense regions of the cosmic web like nodes and clusters. During a merger, The gravitational forces involved can completely reshape the galaxies, transforming spiral galaxies into massive elliptical ones. This process also triggers bursts of star formation, known as starbursts, as gas clouds collide and condense. The Milky Way itself is no stranger to mergers. Throughout its history, the Milky Way has absorbed smaller galaxies, such as the Sagittarius dwarf galaxy, whose remnants can still be traced in the form of stellar streams orbiting the galactic center. In the distant future, the Milky Way will undergo its most significant merger yet, a collision with the Andromeda Galaxy. This event, expected to occur in about 4.5 billion years, will create a new, larger galaxy, likely elliptical in shape, marking a pivotal moment in the history of the local group. While mergers are dramatic, not all interactions lead to such outcomes. Some galaxies experience flybys, where they pass close enough to influence each other gravitationally without merging. These flybys can still have profound effects, such as inducing spiral patterns, altering rotation speeds, or stripping away outer layers of gas and stars. These changes often depend on the relative masses of the galaxies involved. For example, a massive galaxy passing a smaller one can strip the latter of its material entirely, leaving behind a faint, ghostly remnant. In clusters where hundreds or thousands of galaxies coexist in close proximity, interactions are even more frequent. Here, ram pressure stripping becomes a dominant process. As a galaxy moves through the hot, dense gas that fills a cluster, this gas exerts a pressure that can strip away the galaxy's own gas, quenching star formation and leaving the galaxy red and dead. This phenomenon is common in massive clusters like the Coma cluster, where interactions between galaxies and their environment are constant. Interactions are not limited to collisions and gravitational effects. Galaxies also exchange material through gas flows, with streams of gas moving along the filaments of the cosmic web and connecting galaxies. These flows can rejuvenate galaxies by providing fresh material for star formation. Conversely, interactions can also expel material, as winds from supernovae or active galactic nuclei, AGN, blow gas out into intergalactic space. One of the most fascinating aspects of galactic interactions is their role in triggering the growth of supermassive black holes. Nearly every large galaxy, including the Milky Way, harbors a supermassive black hole at its center. During mergers or close encounters, gas is funneled toward the galactic core, fueling the black hole and triggering episodes of intense activity. These active galactic nuclei emit enormous amounts of energy, sometimes outshining the entire galaxy and affecting its evolution by heating surrounding gas and suppressing star formation. While interactions can be destructive, they are also creative. They are responsible for much of the diversity observed in galaxies today, from the elegant spirals of the Milky Way to the massive ellipticals found in clusters. Each collision or interaction reshapes the galaxies involved, mixing stars, redistributing gas, and altering their structures. The remnants of these events can be seen in the form of peculiar galaxies, with warped disks, unusual star clusters, or faint tidal tails stretching across the sky. Modern technology has revolutionized our understanding of galactic interactions. Observatories like the Hubble Space Telescope and the James Webb Space Telescope have captured stunning images of interacting galaxies, providing a window into the processes at work. At the same time, computer simulations have allowed scientists to recreate these events, showing how gravity and physics combine to produce the observed structures. These simulations, such as the Illustris and Eagle projects, have revealed the intricate details of galaxy mergers, from the initial approach to the final coalescence. Despite these advances, many questions remain. For instance, what determines whether a merger results in a spiral or elliptical galaxy? How do interactions in dense clusters differ from those along isolated filaments? And what role do environmental factors, such as the presence of hot gas or magnetic fields, play in shaping the outcomes of these interactions? Galactic interactions are not merely local events. They are part of the broader evolution of the cosmic web. Each collision or merger redistributes material, contributing to the growth of larger structures and the movement of gas and stars across the web. In this way, interactions are a driving force behind the universe's continual transformation, a process that has shaped the cosmos for billions of years and will continue to do so. Reflecting on the interplay of galaxies reminds us of the dynamic nature of the universe. Far from being static or unchanging, galaxies are in constant motion, their fates intertwined with those of their neighbors. These interactions, whether fleeting or catastrophic, are a testament to the interconnectedness of the cosmic web and the forces that govern it. Superclusters, the giants of the web. In the grand hierarchy of the cosmic web, superclusters are its titanic giants, the largest and most massive structures in the universe. These colossal assemblages of galaxies, dark matter, and intergalactic gas span hundreds of millions of light years, serving as the hubs and anchor points of the web's vast filaments. They are not just marvels of scale. Superclusters reveal fundamental truths about the nature of the universe, its evolution, and the forces that govern it. Superclusters are collections of galaxy clusters and groups bound together by gravity. Each cluster contains hundreds or thousands of galaxies, while groups host smaller numbers, all interconnected by the filaments of the cosmic web. The Milky Way, for instance, is part of the Virgo supercluster, itself a substructure of the Laniakea supercluster, an even more massive region spanning over 500 million light-years and containing tens of thousands of galaxies. These immense structures provide a snapshot of the universe's large-scale organization. The formation of superclusters began in the early universe. After the Big Bang, matter was not evenly distributed. Small density fluctuations served as seeds for future structures. Gravity caused these dense regions to grow, pulling in surrounding material and forming the filaments, clusters, and superclusters of the cosmic web. Superclusters emerged where the density of matter was highest, at the intersections of multiple filaments. Over billions of years, these regions grew larger and more massive as they accumulated galaxies and dark matter. Despite their size, superclusters are not permanent structures. They exist in a delicate balance between gravity and the universe's expansion. Gravity pulls galaxies and clusters together, while dark energy, the mysterious force driving the accelerated expansion of the universe, pushes them apart. This cosmic tug-of-war shapes the evolution of superclusters and determines their ultimate fate. Observing superclusters provides valuable insights into the universe's large-scale structure and composition. One key observation method is galaxy surveys, which map the positions of millions of galaxies across the sky. These surveys reveal the clustering of galaxies into filaments and nodes, outlining the boundaries of superclusters. The Sloan Digital Sky Survey, SDSS, for example, has produced detailed three-dimensional maps of the universe, highlighting superclusters like the Sloan Great Wall, one of the largest known structures in the cosmos. Another powerful tool for studying superclusters is gravitational lensing. Massive superclusters warp the fabric of space-time, bending the light from background objects. By analyzing these distortions, astronomers can map the distribution of dark matter within superclusters, which comprises the majority of their mass. These maps not only confirm the presence of dark matter, but also reveal how it is distributed and connected to the galaxies and gas within the supercluster. Superclusters are dynamic systems, with interactions between their constituent clusters and filaments driving their evolution. Galaxy clusters within a supercluster often collide and merge, creating dramatic phenomena. These mergers generate immense shock waves and heat the intergalactic gas to temperatures of tens of millions of degrees, producing X-rays that can be observed with telescopes like Chandra and XMM Newton. These heated regions provide critical insights into the physics of cluster interactions and the role of dark matter in shaping them. The environment within superclusters also influences the galaxies they contain. Galaxies in dense supercluster regions experience frequent interactions and mergers, which can transform their structures and star formation rates. For instance, spiral galaxies may collide and merge into elliptical galaxies, while the hot gas within clusters can strip galaxies of their own gas, halting star formation and leaving them quenched. These processes contribute to the observed differences between galaxies in clusters and those in less dense environments. One of the most remarkable aspects of superclusters is their diversity. Some, like the Shapley supercluster, are extremely dense, containing multiple large clusters and a rich network of filaments. Others, such as the Boötes supercluster, are more diffuse, with widely spaced clusters and less prominent connections. This variety reflects the complex interplay of gravity, dark matter, and cosmic expansion that shapes each supercluster's growth. Superclusters are also central to our understanding of the universe's fate. As dark energy drives the accelerated expansion of space, the filaments connecting superclusters will become increasingly stretched and tenuous. Eventually, this expansion could isolate superclusters from one another, leaving them as isolated islands in an otherwise empty universe. Within individual superclusters, gravity will continue to pull their components together, potentially forming massive singular structures in the far future. Beyond their scientific significance, superclusters invite reflection on the scale and interconnectedness of the universe. They are a reminder of the extraordinary complexity that arises from simple physical laws. From the quantum fluctuations of the early universe to the vast cosmic web, the forces of nature have created structures of staggering beauty and size. Superclusters are not merely assemblages of matter. They are milestones in the universe's journey from simplicity to complexity. Modern observations and simulations continue to refine our understanding of superclusters. Advanced cosmological models, such as the Illustris and Eagle simulations, allow scientists to recreate the formation and evolution of superclusters in virtual universes. These simulations, combined with data from telescopes like the James Webb Space Telescope, are revealing new details about the interplay of dark matter, galaxies, and intergalactic gas. Yet mysteries remain. How do superclusters influence the smaller structures within them? What role do magnetic fields and cosmic rays play in their evolution? And how do their properties vary across the universe? Answering these questions will require even more sophisticated instruments and observations, as well as new theoretical approaches. Superclusters, the giants of the cosmic web, are both awe-inspiring and humbling. They are the scaffolds of the universe's largest structures, the hubs of activity in a network that spans billions of light years. By studying these immense systems, we gain not only a deeper understanding of the cosmos, but also a greater appreciation for the forces that have shaped it. In their scale and grandeur, superclusters remind us of the extraordinary complexity of the universe and our own small yet significant place within it. The cosmic web in computer simulations. While the cosmic web stretches across billions of light years, its intricacies remain hidden from direct observation. The vast scale, the dominance of dark matter, and the faintness of intergalactic structures make it challenging to study the web in its entirety. However, computer simulations have become a powerful tool for unraveling its mysteries. These simulations allow scientists to model the evolution of the universe, recreating the birth and growth of the cosmic web with remarkable accuracy. The foundation of these simulations lies in our understanding of physics and cosmology, starting with the initial conditions of the early universe, imprinted by the Big Bang and observed in the cosmic microwave background, CMB. Simulations use the laws of gravity, hydrodynamics, and thermodynamics to predict how matter and energy evolve over billions of years. These models incorporate the interplay of dark matter, ordinary matter, and dark energy, capturing the processes that give rise to the web's filaments, nodes, and voids. One of the most groundbreaking simulations was the Millennium Simulation, conducted in 2005. This large-scale project modeled the evolution of dark matter and galaxies in a cubic region of space over 2 billion light-years across. By tracking the behavior of billions of particles representing dark matter, the simulation revealed a strikingly realistic depiction of the cosmic web, including its intricate network of filaments and clusters. The Millennium Simulation provided a foundation for subsequent studies, demonstrating the power of simulations to replicate and predict the universe's large-scale structure. More recent projects, such as the Illustris and Eagle simulations, have expanded on this work by incorporating additional physics. These simulations model not only dark matter, but also ordinary matter, including gas, stars, and supermassive black holes. This added complexity allows scientists to study the detailed processes that shape galaxies, such as star formation, feedback from supernovae, and the influence of black holes on their surroundings. The results are stunningly detailed virtual universes that mirror the observed properties of galaxies and the cosmic web. One of the key insights from these simulations is the role of dark matter in sculpting the web. Dark matter provides the gravitational framework for the universe, pulling ordinary matter into filaments and nodes where galaxies and clusters form. Simulations show that without dark matter, the cosmic web as we know it could not exist. The distribution of dark matter determines the locations of filaments and clusters, while its interactions drive the flow of material along the web. Simulations have also shed light on the formation of voids, the vast, empty regions between filaments. These voids grow as gravity pulls matter into denser regions, leaving behind expanses of low-density space. By studying the behavior of voids in simulations, scientists can better understand the processes that shape the cosmic web on the largest scales. For instance, simulations reveal how voids evolve over time, becoming increasingly empty as the universe expands. Another critical application of simulations is testing theories of dark energy. By comparing the growth of structure in simulated universes with different dark energy models, scientists can explore how this mysterious force influences the cosmic web. These comparisons help refine our understanding of dark energy's properties and its impact on the universe's expansion. Simulations also provide a unique perspective on the history of the cosmic web. By rewinding the evolution of simulated structures, researchers can trace the origins of galaxies, clusters, and filaments back to the early universe. This approach allows scientists to reconstruct the web's formation, revealing how initial density fluctuations grew into the vast network we observe today. It also highlights the hierarchical nature of the web, where small structures form first and gradually merge into larger ones. Despite their successes, simulations are not without limitations. The complexity of the universe requires simplifications and approximations, and some processes, such as star formation and black hole activity, are not fully understood. These uncertainties can affect the accuracy of the results, particularly on small scales where detailed physics becomes crucial. Additionally, the sheer scale of simulations requires immense computational power, limiting the size and resolution of the models. To address these challenges, scientists are developing next-generation simulations that push the boundaries of computational capability. Projects like SIMBA and Illustrious TNG aim to model even larger volumes of the universe with higher resolution, capturing finer details of the cosmic web. These simulations also incorporate more sophisticated physics, such as the effects of magnetic fields, cosmic rays, and detailed models of feedback processes. The integration of machine learning and artificial intelligence, AI, is another exciting frontier in simulation science. AI algorithms can analyze vast amounts of data from simulations, identifying patterns and correlations that might otherwise go unnoticed. These tools also help optimize simulations, improving their efficiency and accuracy. For example, AI has been used to create emulators that predict the outcomes of simulations without the need for extensive calculations, enabling faster exploration of parameter spaces. Simulations are not only scientific tools, but also sources of inspiration and discovery. They allow us to visualize the cosmic web in ways that are impossible with observations alone, bringing its hidden structures to life. The images and animations produced by simulations, from swirling galaxy clusters to sprawling filaments, capture the beauty and complexity of the universe, inspiring both scientists and the public. Looking ahead, the future of simulations is intertwined with the next generation of telescopes and observational programs. Projects like the Vera C. Rubin Observatory, the James Webb Space Telescope, and the Euclid mission will provide unprecedented data on the cosmic web, offering new opportunities to test and refine simulations. By combining the strengths of observations and simulations, scientists will gain deeper insights into the universe's structure, composition, and evolution. The cosmic web in simulations is a testament to the power of human ingenuity and curiosity. It allows us to explore the universe on scales that are otherwise inaccessible, revealing the hidden forces and processes that shape the cosmos. Each simulation brings us closer to understanding the cosmic web's origins and its role in the universe's grand narrative, a story of structure, connection, and the relentless pull of gravity across the vastness of space. Theories on cosmic web formation. The cosmic web, a sprawling network of filaments, nodes, and voids, is one of the universe's most awe-inspiring structures. Its formation is a tale of physics and cosmology spanning billions of years, shaped by the interplay of gravity, dark matter, and the universe's expansion. While much of its development is well understood, the precise mechanisms that underlie its formation remain the subject of active research and debate. What theories explain the birth of the cosmic web, and how have these ideas evolved over time? The roots of cosmic web formation lie in the early universe, shortly after the Big Bang. The Big Bang theory, our foundational framework for understanding the cosmos, posits that the universe began as a hot, dense, and nearly uniform state. However, observations of the cosmic microwave background, CMB, reveal that this uniformity was not absolute. Instead, tiny fluctuations in temperature and density, on the order of 1 part in 100,000, dotted the young universe. These fluctuations, or quantum perturbations, are the seeds of the cosmic web. The theory of cosmic inflation, which describes a brief but exponential expansion of the universe shortly after the Big Bang, provides an explanation for their origin. During inflation, quantum fluctuations in space-time were stretched to macroscopic scales, imprinting the universe with regions of slightly higher and lower density. These tiny differences would later be amplified by gravity, leading to the large-scale structures we observe today. As the universe expanded and cooled, the first critical step in web formation occurred: recombination. Approximately 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light to travel freely. The resulting CMB carries the imprint of the initial density fluctuations, offering a snapshot of the universe's earliest structures. From this starting point, the process of gravitational instability took over. Regions of higher density exerted a stronger gravitational pull, attracting more matter and growing over time. Meanwhile, less dense regions lost material to their denser counterparts, becoming the voids we see today. This self-reinforcing process, known as structure formation, lies at the heart of cosmic web development. One of the most significant advancements in understanding cosmic web formation came with the introduction of dark matter. Observations of galaxy rotation curves and galaxy cluster dynamics revealed that visible matter alone could not account for the gravitational forces at play. Instead, an unseen form of matter, dark matter, dominates the mass of the universe, shaping its large-scale structure. Dark matter's role in web formation is central. Unlike ordinary matter, which interacts through electromagnetic forces and can dissipate energy, dark matter interacts only gravitationally. This lack of interaction allows dark matter to form vast, diffuse structures, providing the scaffolding for the cosmic web. Theories suggest that dark matter clumped together into halos, regions of high density that served as the anchors for galaxies and clusters. The behavior of dark matter is described by the cold dark matter (CDM) model, which posits that dark matter particles are cold, moving slowly compared to the speed of light, and thus prone to clustering. This model explains the hierarchical nature of the cosmic web, where small structures form first and merge into larger ones over time. CDM simulations, such as the Millennium simulation, have shown that the web's filaments and nodes naturally emerge from this process, matching observations with remarkable accuracy. An alternative theory, warm dark matter (WDM), posits that dark matter particles move more quickly, suppressing the formation of smaller structures. While WDM could resolve certain discrepancies between CDM predictions and observations, such as the number of small galaxies, it struggles to replicate the detailed features of the cosmic web. As a result, CDM remains the leading framework for understanding web formation. The inclusion of baryonic matter, the ordinary matter that makes up stars, gas, and planets, adds another layer of complexity. While dark matter dominates the web structure, baryonic matter interacts through electromagnetic forces, leading to processes like cooling, condensation, and star formation. The movement of baryonic matter along the web's filaments fuels the growth of galaxies and clusters, enriching the web with luminous structures. The role of dark energy further complicates the picture. Discovered through the accelerating expansion of the universe, dark energy opposes gravity, pushing matter apart. This force affects the cosmic web by slowing the growth of structures and stretching its filaments. Theories of web formation must account for this interplay between gravity and dark energy, which shapes the web's evolution over billions of years. Emerging theories and observations continue to refine our understanding of the cosmic web's formation. For instance, studies of the Lyman alpha forest, patterns of hydrogen absorption in the spectra of distant quasars, offer insights into the distribution of gas along filaments. These observations provide a direct link between theoretical models and the web's actual structure. Computer simulations have become an indispensable tool for testing theories of web formation. Projects like Illustrious TNG and Eagle incorporate detailed physics, including the effects of black holes, star formation, and feedback processes, to model the web's development. These simulations not only validate existing theories, but also generate predictions that guide future observations. Despite these advancements, key questions remain. What is the true nature of dark matter, and how does it influence the web's smallest scales? How does the interplay between baryonic matter and dark matter shape the web's detailed features? And what role do magnetic fields, cosmic rays, and other phenomena play in the web's evolution? Theoretical models also face challenges in explaining certain observations, such as the alignment of galaxies within filaments or the properties of the largest voids. These discrepancies suggest that additional factors, perhaps related to the nature of dark energy or alternative theories of gravity, may be at play. Theories on cosmic web formation are more than abstract models. They are a window into the universe's deepest truths. They connect the physics of the infinitesimally small, such as quantum fluctuations, with the vast structures spanning billions of light years. Each discovery, from the nature of dark matter to the effects of dark energy, adds a new thread to the tapestry, bringing us closer to a complete understanding of the cosmic web. Reflecting on the cosmic web's formation invites us to ponder the delicate balance of forces that created the universe's grand structure. From the quantum seeds of the Big Bang to the sprawling filaments of today, the web story is one of connection and complexity, a testament to the power of physics to shape the cosmos on the grandest scales. Quantum roots, the smallest scales of the web, the cosmic web's grandeur, spanning billions of light years, originates from something astonishingly small: quantum fluctuations in the early universe. These minuscule variations in energy density, amplified over billions of years by gravity, are the foundational seeds of the sprawling network of filaments, nodes, and voids we observe today. To understand the cosmic web's true beginnings, we must delve into the realm of quantum mechanics, where the universe's largest structures find their roots in its smallest scales. The story begins during the inflationary era, a fleeting but transformative moment in the universe's history. Inflation, occurring a fraction of a second after the Big Bang, describes a period of exponential expansion that smoothed out the universe and set the stage for the formation of structure. During this epoch, quantum fluctuations, tiny random variations in energy, were stretched to macroscopic scales. These fluctuations, once confined to subatomic spaces, became the density perturbations that would later evolve into the cosmic web. Quantum fluctuations arise from the principles of quantum mechanics, which govern the behavior of particles and fields at the smallest scales. In this framework, energy is never perfectly uniform or static. Instead, it fluctuates constantly, creating temporary regions of higher or lower energy density. Under normal circumstances, these fluctuations are confined to the microscopic world, but during inflation, the universe's rapid expansion magnified them, imprinting them onto the fabric of space-time. These imprints, known as primordial density perturbations, are preserved in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB provides a snapshot of the universe as it existed roughly 380,000 years after the Big Bang, when photons were first able to travel freely through space. Its subtle variations in temperature and density reflect the quantum fluctuations that were stretched during inflation, revealing the seeds of the structures that would eventually form the cosmic web. The properties of these fluctuations are remarkably uniform, yet slightly irregular, a balance that is critical for the universe's evolution. If the fluctuations were too small, gravity would not have been able to amplify them into the large-scale structures we see today. Conversely, if they were too large, the universe would have collapsed into massive black holes or hyperdense regions. The precise spectrum of these fluctuations, a nearly scale-invariant pattern, matches the predictions of inflationary theory and provides strong evidence for this model. The growth of these tiny perturbations into the cosmic web involves a multi-step process governed by the interplay of physics on vastly different scales. In the early universe, these density variations served as gravitational wells, pulling in surrounding matter. This process began with dark matter, which does not interact with light or ordinary matter, but exerts gravitational influence. Dark matter clumped together into halos, creating the scaffolding for the cosmic web. Ordinary matter, composed of protons, neutrons, and electrons, followed the dark matter's lead, falling into these gravitational wells. However, unlike dark matter, ordinary matter interacts through electromagnetic forces, leading to additional complexities. As it fell into the wells, it heated up and formed pressure waves, creating oscillations known as baryon acoustic oscillations, BAOs. These oscillations left imprints in the distribution of matter, creating a characteristic scale that is still visible in the arrangement of galaxies and clusters today. The role of quantum fluctuations extends beyond the formation of the cosmic web. They also provide insights into the universe's fundamental physics. For instance, the properties of these fluctuations depend on the nature of the inflationary field, the mysterious energy source that drove inflation. By studying the CMB and the large-scale structure of the universe, scientists can constrain the parameters of inflationary models, shedding light on the physics of the very early universe. One intriguing aspect of quantum fluctuations is their connection to multiverse theories. Some models of inflation suggest that our universe is just one of many, each with its own unique set of fluctuations and physical laws. In this view, the cosmic web we observe is a product of the particular fluctuations that occurred in our universe's inflationary epoch, while other universes may have entirely different structures. Despite the successes of inflationary theory, questions remain about the quantum roots of the cosmic web. For example, the precise mechanism that generated inflation is still unknown, as is the nature of the inflationary field itself. Additionally, while quantum fluctuations provide the initial seeds for structure, they do not explain why the universe's density is so finely balanced, a mystery often referred to as the flatness problem. These unanswered questions drive ongoing research in both cosmology and fundamental physics. Advances in observational technology are helping to refine our understanding of these quantum beginnings. Instruments like the Planck satellite have provided exquisitely detailed maps of the CMB, revealing the tiny temperature variations imprinted by primordial fluctuations. Upcoming missions, such as the Simons Observatory and the CMB S4 experiment, aim to detect even fainter signals, including the polarization patterns in the CMB that could reveal more about inflation and the quantum origins of the web. Computer simulations also play a vital role in linking quantum fluctuations to the cosmic web. By starting with the density perturbations observed in the CMB, simulations can model the growth of structure over billions of years, reproducing the web's filaments, nodes, and voids. These simulations, such as Illustris and Eagle, provide a bridge between the smallest and largest scales of the universe, connecting quantum physics with cosmological structure. Reflecting on the quantum roots of the cosmic web is a humbling reminder of the universe's interconnectedness. The vast filaments and sprawling clusters we observe today owe their existence to phenomena occurring at the smallest conceivable scales. From the randomness of quantum fluctuations to the vastness of the cosmic web, the universe is a testament to the profound interplay of simplicity and complexity. The study of quantum origins also underscores the power of science to uncover the deepest truths about the cosmos. By connecting the physics of the subatomic world with the structure of the universe, researchers are building a comprehensive picture of how the cosmos evolved from its earliest moments to its present state, a story written in the language of quantum mechanics and played out on the grandest of stages. The role of neutrinos in the cosmic web. Neutrinos, the elusive and nearly massless particles often called the ghosts of the universe, are among the most abundant particles in existence. Trillions pass through every square centimeter of your body every second. Yet they interact so weakly with matter that they are nearly impossible to detect. Despite their ghostly nature, neutrinos play a subtle but critical role in the evolution of the universe, including the formation and structure of the cosmic web. The story of neutrinos begins in the early universe, mere seconds after the Big Bang. During this epoch, the universe was a hot, dense plasma of particles and radiation. Neutrinos, created in abundance during nuclear reactions in the Big Bang, decoupled from the rest of the matter and radiation just a few seconds after the universe's birth, forming what is known as the cosmic neutrino background. These relic neutrinos still exist today, though they are incredibly faint and difficult to detect directly. In the context of the cosmic web, neutrinos are unique because of their tiny masses and high velocities. Unlike dark matter, which moves slowly and clumps together to form the backbone of the cosmic web, neutrinos are classified as hot dark matter due to their relativistic speeds in the early universe. This characteristic allows neutrinos to stream freely across vast distances, smoothing out density fluctuations and suppressing the formation of small-scale structures. The impact of neutrinos on the cosmic web is most evident in their role as structure dampers. While cold dark matter, CDM, encourages the growth of small structures, neutrinos act as a counterforce, suppressing the formation of structures below a certain scale. This effect creates a characteristic pattern in the large-scale structure of the universe, with fewer small halos and filaments than would be expected in a universe without neutrinos. The influence of neutrinos becomes more pronounced as their mass increases. Though neutrinos are extremely light, each weighing less than a millionth of the mass of an electron, recent experiments suggest that their combined mass, summed over all three neutrino species, may have measurable effects on the universe's structure. By studying these effects, cosmologists can place constraints on the masses of neutrinos, an achievement that connects the realms of particle physics and cosmology. One of the most significant observational tools for studying neutrinos' impact on the cosmic web is the cosmic microwave background, CMB. Subtle imprints left by neutrinos on the CMB provide clues about their properties, such as their mass and abundance. For instance, the presence of neutrinos alters the rate of expansion in the early universe, affecting the CMB's temperature fluctuations and polarization patterns. By analyzing these imprints, scientists have inferred that neutrinos contribute to the total energy density of the universe and have placed upper limits on their masses. The large-scale structure of the universe, as mapped by galaxy surveys, also offers insights into neutrino physics. Neutrinos' ability to suppress small-scale structure creates a fingerprint in the distribution of galaxies, clusters, and filaments. By comparing observations of the cosmic web with simulations that include neutrinos, scientists can refine their understanding of how these particles shape the universe. One intriguing consequence of neutrinos' role in the cosmic web is their potential connection to the missing satellites problem. The discrepancy between the number of small galaxies predicted by simulations and those observed in the universe. Neutrino suppression of small-scale structure may partially explain this mismatch, as their smoothing effect reduces the number of small halos in which galaxies can form. The interplay between neutrinos and the cosmic web extends to the dynamics of galaxy clusters, the largest gravitationally bound structures in the universe. Neutrinos influence the growth rate of clusters by slowing the accumulation of mass. Observations of cluster dynamics, combined with measurements of gravitational lensing, provide additional constraints on neutrino properties. Detecting the cosmic neutrino background directly remains one of the most significant challenges in physics. These relic neutrinos are far colder and less energetic than their high-energy counterparts produced in stars, supernovae, and particle accelerators. However, experiments like Ptolemy aim to detect these ancient particles, potentially opening a new window into the early universe and the role of neutrinos in shaping its structure. The study of neutrinos in the cosmic web highlights the interconnectedness of fundamental physics and cosmology. Neutrinos, despite their minuscule masses and weak interactions, have a measurable impact on the universe's largest structures. This interplay between the smallest and largest scales underscores the importance of neutrinos in the grand cosmic narrative. Looking ahead, Advances in both observational and experimental techniques will continue to refine our understanding of neutrinos and their role in the cosmos. Projects like the Euclid mission and the Nancy Grace Roman Space Telescope aim to map the universe's structure with unprecedented precision, providing new opportunities to study the fingerprints of neutrinos. At the same time, laboratory experiments in particle physics will probe the fundamental properties of neutrinos, bridging the gap between microphysics and cosmic structure. The role of neutrinos in the cosmic web is a reminder of the profound connections that link the universe's smallest particles with its grandest structures. From their origins in the Big Bang to their influence on the evolution of galaxies and clusters, neutrinos are a testament to the power of physics to shape the cosmos. In their elusive nature, they embody the mysteries that drive our exploration of the universe, offering glimpses into the hidden forces that govern its evolution. Galactic migration across the web. The universe is in constant motion, and galaxies, the luminous markers of the cosmic web, are no exception. Across billions of light years, galaxies travel along the filaments of the web, pulled by gravity and guided by the underlying scaffolding of dark matter. This movement, known as galactic migration, plays a crucial role in shaping the structure and evolution of galaxies, clusters, and the web itself. But what drives this migration, and how does it influence the grand tapestry of the cosmos? Galactic migration begins with the gravitational dynamics of the cosmic web. The web's filaments and nodes are regions of higher density, where matter has accumulated over billions of years. These structures exert a gravitational pull on nearby galaxies, drawing them along the filaments toward denser regions, such as galaxy clusters or superclusters. This process is akin to rivers flowing into lakes, with galaxies moving through the filaments like water streams drawn to larger basins. The migration of galaxies is not random. Their paths are determined by the web's intricate geometry, which is itself shaped by the distribution of dark matter. Galaxies follow the filaments like vehicles on intergalactic highways, their trajectories influenced by the gravitational landscape. As they move, galaxies can pass through multiple environments, from the sparse outskirts of filaments to the crowded hubs of clusters, experiencing a wide range of interactions along the way. One of the most significant effects of galactic migration is galaxy transformation. As galaxies move through different regions of the web, their structures and behaviors can change dramatically. For example, in the dense environments of filaments and clusters, galaxies often experience ram pressure stripping, where interactions with hot, intergalactic gas remove their own gas reservoirs. This process halts star formation, leaving behind quenched galaxies dominated by older, redder stars. Galaxy mergers and interactions are another key consequence of migration. As galaxies move along filaments, they are more likely to encounter one another, especially near the nodes where multiple filaments intersect. These interactions can range from gentle gravitational influences that distort a galaxy's shape to full-fledged collisions that trigger bursts of star formation, or even result in the merging of two galaxies into a single, larger system. The Milky Way itself is a participant in this cosmic migration. Located within a filament of the local group, our galaxy is slowly moving toward the Andromeda Galaxy, a motion that will culminate in a merger approximately 4.5 billion years from now. Beyond the local group, the entire Milky Way is being drawn toward the Great Attractor, a dense region within the Laniakea supercluster. These movements reflect the gravitational currents that permeate the cosmic web, guiding galaxies over immense timescales. Galactic migration also has profound effects on the cosmic web itself. As galaxies move through filaments, they transport gas, dust, and dark matter, redistributing material across the web. This flow of material influences the web's evolution, shaping the sizes and densities of filaments and nodes. Over time, these processes contribute to the web's hierarchical growth, with smaller structures merging into larger ones. The velocity of galactic migration provides valuable insights into the dynamics of the universe. By measuring the speeds of galaxies as they move along filaments or fall into clusters, astronomers can infer the distribution of dark matter and the influence of dark energy. For example, the peculiar velocity field, which maps deviations from the overall expansion of the universe, reveals how galaxies move in response to the gravitational pull of the web structures. Observing galactic migration requires advanced techniques and instruments. Redshift surveys, such as those conducted by the Sloan Digital Sky Survey (SDSS), map the positions and motions of millions of galaxies, creating three-dimensional views of their distribution and movement. Gravitational lensing, where the light from distant galaxies is bent by intervening mass, provides additional clues about the web's underlying structure and the paths of migrating galaxies. Computer simulations are another crucial tool for studying galactic migration. By modeling the evolution of the cosmic web, these simulations reveal how galaxies move over billions of years, from their initial formation to their incorporation into clusters and superclusters. Projects like Illustrious TNG and Eagle have provided detailed visualizations of galactic flows, highlighting the interactions between galaxies, gas, and dark matter. Galactic migration also influences the creation of cosmic streams, rivers of stars and gas that trace the movements of galaxies and their interactions. These streams, often the remnants of smaller galaxies disrupted by larger ones, provide a record of past migrations and encounters. Observing these streams offers insights into the history of individual galaxies and the dynamics of the web. Despite its importance, many aspects of galactic migration remain poorly understood. For instance, how do the properties of a filament, such as its density or orientation, affect the speed and direction of galactic movement? What role do magnetic fields and cosmic rays play in shaping the trajectories of galaxies? And how does the interplay between dark matter and ordinary matter influence the overall dynamics of migration? The future of research on galactic migration will be driven by the next generation of telescopes and observatories. The Rubin Observatory, with its ability to survey the entire sky, will provide an unprecedented view of the motions of galaxies across the cosmic web. Similarly, missions like Euclid and the Nancy Grace Roman Space Telescope will map the distribution of dark matter and the flow of galaxies with unparalleled precision. Galactic migration is more than a mechanical process. It is a narrative of motion, transformation, and connection. Each galaxy's journey across the web is shaped by its environment and interactions, contributing to the universe's evolving structure. From the smallest dwarf galaxies to the largest superclusters, every component of the web participates in this grand cosmic dance. Reflecting on galactic migration offers a deeper appreciation of the dynamic nature of the universe. Far from being static, the cosmic web is alive with motion, its filaments and nodes constantly reshaped by the flow of galaxies and matter. This perpetual movement underscores the interconnectedness of the cosmos, where every galaxy is part of a larger whole, traveling through the vast network of the web. The intergalactic medium, bridging the filaments. The intergalactic medium, IGM, is the vast, diffuse expanse of gas and plasma that fills the spaces between galaxies. Though largely invisible to the naked eye, the IGM is one of the universe's most critical components, acting as both the connective tissue of the cosmic web and the reservoir from which galaxies draw their material. It bridges the filaments, linking galaxies and clusters, and plays a central role in the cosmic web's formation and evolution. What is the IGM, and how does it influence the dynamics of the universe? The IGM primarily consists of hydrogen and helium, the simplest and most abundant elements in the universe. These elements were forged in the Big Bang and remained in gaseous form, unincorporated into stars or galaxies, for much of the universe's early history. Over billions of years, the IGM has evolved under the influence of gravity, radiation, and cosmic expansion, forming the filaments and nodes of the cosmic web. The distribution of the IGM is not uniform. It follows the large-scale structure of the universe, with higher densities found along filaments and in galaxy clusters, while vast voids contain little more than a tenuous sprinkling of particles. Along the filaments, the IGM acts as a conduit for matter, channeling gas into galaxies and clusters where it fuels star formation and other processes. In this sense, the IGM is both a passive scaffold and an active participant in the universe's evolution. The physical state of the IGM varies depending on its location and the surrounding environment. In low-density regions, the IGM is cool and neutral, composed mainly of atomic hydrogen. Along the denser filaments and in clusters, it becomes heated and ionized, reaching temperatures of millions of degrees due to shocks and gravitational compression. This hot, ionized gas is often referred to as the warm-hot intergalactic medium, WIM, and is one of the most elusive components of the universe. One of the IGM's most important roles is as a source of gas for galaxies. Galaxies rely on the inflow of fresh material from the IGM to sustain star formation and maintain their growth. This gas flows along the filaments, gradually accreting onto galaxies and contributing to the formation of new stars. Without this constant supply, galaxies would exhaust their gas reserves and become quiescent. The IGM also acts as a bridge between galaxies, facilitating the exchange of material. For example, during galaxy mergers or interactions, gas can be stripped from galaxies and deposited into the IGM. This expelled gas can later cool and rejoin the galactic environment, completing a cycle of material exchange that connects galaxies to their surroundings. Observing the IGM directly is challenging due to its diffuse and faint nature. However, several methods have been developed to detect and study it. One of the most effective techniques involves observing the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars. As light from a quasar passes through the IGM, it is absorbed by hydrogen at specific wavelengths, creating a forest of spectral lines that reveals the distribution and density of gas along the line of sight. Gravitational lensing provides another way to study the IGM. The IGM's mass, though spread thinly, can bend the light from background sources, creating subtle distortions in their appearance. By analyzing these distortions, astronomers can infer the distribution of gas and dark matter in the cosmic web. The IGM's interaction with galaxies and the cosmic web is deeply influenced by feedback processes. When stars and black holes release energy through supernova explosions, stellar winds, or active galactic nuclei, AGN, they inject heat and momentum into the surrounding gas. This feedback can expel gas from galaxies, enriching the IGM with heavier elements like carbon and oxygen. These metals, forged in stars, serve as tracers for studying the movement and composition of the IGM. The IGM also plays a crucial role in the universe's thermal history. During the reionization era, beginning around 100 million years after the Big Bang, ultraviolet light from the first stars and galaxies ionized the neutral hydrogen in the IGM, transforming it into a hot, ionized state. This process marked a significant phase transition in the universe, allowing light to travel freely through space and shaping the IGM's current state. Modern observations have revealed that a significant portion of the universe's ordinary matter resides in the IGM. This finding resolves a long-standing mystery known as the missing baryon problem, which referred to the discrepancy between the amount of ordinary matter predicted by cosmological models and the amount observed in galaxies and clusters. The WIM, in particular, accounts for much of this missing matter, though detecting it requires advanced X-ray and ultraviolet telescopes. The interplay between the IGM and the cosmic web is a dynamic and ongoing process. As the universe expands, the IGM evolves, with filaments stretching and voids growing emptier. At the same time, the flow of gas within the IGM continues to shape galaxies, clusters, and the web itself. These processes highlight the IGM's dual role as both a product of the cosmic web and a driver of its evolution. Future studies of the IGM will benefit from next-generation telescopes and observatories. The James Webb Space Telescope, JWST, the Vera C. Rubin Observatory, and the Athena X-ray Observatory are expected to provide unprecedented views of the IGM, from the cool gas and voids to the hot plasma and filaments and clusters. Combined with simulations and theoretical models, these observations will deepen our understanding of the IGM's role in the universe. Reflecting on the intergalactic medium offers a deeper appreciation of the connections that define the cosmic web. Though invisible and diffuse, the IGM is a vital part of the universe's story, linking galaxies and clusters and sustaining their growth. It is a reminder that even in the vast emptiness of space, there is an unseen network of connections shaping the cosmos. The cosmic web and the origins of life. The cosmic web, with its intricate network of filaments, nodes, and voids not only governs the large-scale structure of the universe, but may also hold clues to one of the most profound questions in science: the origins of life. While life as we know it exists on the relatively small scale of planets and stars, the conditions that make life possible are inextricably linked to the processes and structures of the cosmic web. Could the grand architecture of the universe play a role in determining where and how life arises? The cosmic web's connection to the origins of life begins with the formation of stars and galaxies. These luminous structures, nestled within the dense nodes and filaments of the web, are the cradles of planets and the chemical elements necessary for life. The earliest stars, composed almost entirely of hydrogen and helium, forged heavier elements like carbon, oxygen, and nitrogen in their cores through nuclear fusion. When these stars died in explosive supernovae, they scattered these elements into the surrounding interstellar medium, enriching the gas that would later form new stars and planets. The locations of stars and galaxies within the cosmic web influence their ability to foster life. In dense regions like galaxy clusters, frequent interactions between galaxies can disrupt star systems, stripping away gas needed for planet formation and creating environments hostile to the development of life. Conversely, in more isolated regions along filaments or in smaller galaxy groups, the conditions may be more stable, allowing for the formation of planetary systems capable of supporting life. The intergalactic medium, IGM, the diffuse gas that bridges the filaments of the cosmic web, also plays a crucial role. This gas is the reservoir from which galaxies draw material to form stars and planets. The inflow of gas along filaments fuels star formation, while the outflows from supernovae and active galactic nuclei enrich the surrounding medium with heavier elements. This cycle of material within the cosmic web ensures a steady supply of the building blocks necessary for life. One of the most intriguing aspects of the cosmic web's role in the origins of life is its influence on the distribution of habitable environments. Planets capable of supporting life require specific conditions, such as liquid water, a stable atmosphere, and a source of energy. These conditions depend on the properties of the host star, the planet's position within its solar system, and the larger galactic environment. The cosmic web indirectly shapes these factors by determining the distribution and evolution of galaxies and stars. For instance, the metallicity of a star, its abundance of elements heavier than hydrogen and helium, affects its potential to host habitable planets. Stars with higher metallicity are more likely to form planets, particularly rocky ones like Earth. The metallicity of stars, in turn, depends on their position within the cosmic web. Dense regions, where star formation has been active for billions of years, tend to have higher metallicity than less dense areas, creating a gradient of potential habitability across the web. The cosmic web also influences the radiation environment of galaxies and planets. In clusters and along dense filaments, galaxies are often exposed to higher levels of radiation from supernovae, quasars, and active galactic nuclei. This radiation can strip away planetary atmospheres or damage emerging biospheres, making these regions less hospitable to life. On the other hand, more isolated regions of the web may offer safer environments, shielded from the intense radiation of active galactic processes. Cosmic rays, high-energy particles that travel through the universe, provide another connection between the cosmic web and the origins of life. Generated by supernovae and other energetic events, cosmic rays can influence the chemistry of planetary atmospheres, potentially playing a role in the synthesis of complex organic molecules. The flux of cosmic rays varies across the cosmic web, depending on a galaxy's position and the activity within its environment. The cosmic web's role in shaping the origins of life extends beyond the distribution of habitable environments. It also provides a framework for understanding the cosmic context of life's emergence. The web's structure reflects the fundamental forces and processes that have governed the universe since its inception, from the quantum fluctuations of the Big Bang to the gravitational dynamics of dark matter. By studying the cosmic web, scientists gain insights into the conditions that have shaped not only the universe's structure, but also its potential to harbor life. One of the most profound questions in this context is whether life is unique to Earth or a widespread phenomenon. If life requires specific conditions that depend on the structure of the cosmic web, it may be more likely to arise in certain regions of the universe than others. For example, galaxies located in relatively stable, low-density regions of the web might have a higher likelihood of hosting life-friendly planets than those in turbulent cluster environments. The search for extraterrestrial life is increasingly informed by our understanding of the cosmic web. Missions like the James Webb Space Telescope (JWST) are designed to study the atmospheres of exoplanets, searching for biosignatures, chemical markers of life. By mapping the distribution of potentially habitable exoplanets across the galaxy, scientists can explore how the cosmic web structure influences the likelihood of life's emergence. Theoretical models and simulations also play a critical role in linking the cosmic web to the origins of life. By incorporating the physics of galaxy formation, star formation, and chemical enrichment, simulations like Illustrious TNG provide a framework for understanding how the web shapes the distribution of habitable environments. These models offer a way to test hypotheses about the connection between the universe's large-scale structure and the conditions necessary for life. Despite the progress made, many questions remain. How do the dynamics of the cosmic web influence the evolution of planetary systems over billions of years? What role do intergalactic processes, such as the flow of gas along filaments, play in shaping the environments where life could emerge? And could life itself, once established, have an impact on the evolution of the cosmic web, perhaps through the activities of advanced civilizations? The cosmic web and the origins of life are deeply interconnected, highlighting the unity of the universe's largest and smallest scales. From the distribution of galaxies and stars to the formation of planets and the emergence of living organisms, the web provides a framework for understanding how the cosmos supports the phenomenon of life. Reflecting on this connection invites us to consider our place within the universe, as both observers of its grand design and participants in its ongoing story. Observational milestones. A brief history. The journey to uncover the cosmic web is one of the most remarkable sagas in the history of astronomy. It began with early efforts to map the night sky and has culminated in sophisticated observations of the universe's largest structures. Each milestone in this journey has brought us closer to understanding the vast, interconnected network of galaxies, filaments, and voids that define the cosmos. How did humanity come to recognize the cosmic web, and what have been the key breakthroughs along the way? The first hints of structure in the universe emerged with the development of telescopic astronomy in the 17th and 18th centuries. Early astronomers like Galileo and William Herschel observed that stars were not distributed evenly across the sky, but concentrated in patterns, forming what we now know as the Milky Way galaxy. Herschel's surveys, which cataloged thousands of stars and nebulae, laid the groundwork for the idea that the universe contained large-scale structures. The discovery of galaxies as distinct entities was another crucial step. In the early 20th century, astronomers like Edwin Hubble and Vesto Slipher identified spiral nebulae as galaxies beyond the Milky Way. Hubble's observations, combined with Slipher's measurements of galaxy redshifts, revealed that the universe was expanding. This discovery, coupled with Hubble's classification of galaxies, provided the first glimpse of the universe as a dynamic and structured system. As telescopes improved, astronomers began to notice that galaxies were not evenly distributed but clustered together in groups and clusters. Observations in the mid-20th century, such as those conducted by Fritz Zwicky, highlighted the existence of galaxy clusters and hinted at the presence of unseen dark matter that held these structures together. The discovery of the Coma cluster, a dense concentration of galaxies, revealed the gravitational forces at play on large scales. The advent of large-scale galaxy surveys in the late 20th century marked a turning point in our understanding of the cosmic web. The CFA Redshift Survey, conducted in the 1980s, mapped the positions of thousands of galaxies in 3 dimensions, revealing the filamentary and clumpy nature of the universe. These surveys provided the first direct evidence of the cosmic web structure, showing how galaxies were arranged along filaments and clustered at their intersections. The Sloan Digital Sky Survey (SDSS), launched in 2000, revolutionized the field by mapping millions of galaxies across the sky with unprecedented detail. The SDSS produced striking images of the large-scale structure of the universe, including features like the Sloan Great Wall, a massive filament of galaxies stretching over 1 billion light-years. These observations confirmed that the cosmic web was not just a theoretical construct, but a tangible feature of the universe. Advancements in technology also enabled astronomers to study the cosmic web beyond the visible spectrum. X-ray telescopes like Chandra and XMM Newton revealed the hot gas and galaxy clusters and filaments, providing insights into the distribution of baryonic matter. Observations in the radio and ultraviolet wavelengths, such as those conducted by the South Pole Telescope and the Very Large Array, uncovered details about the intergalactic medium and the role of cosmic rays in the web. The study of the cosmic microwave background, CMB, the faint afterglow of the Big Bang, has been another critical milestone. Missions like COBE, WMAP, and Planck have mapped the CMB with increasing precision, revealing the initial density fluctuations that gave rise to the cosmic web. These fluctuations, imprinted on the CMB, provide a blueprint of the web's formation and evolution, connecting the universe's earliest moments to its present-day structure. The discovery of dark energy in the late 1990s added a new dimension to our understanding of the cosmic web. Observations of Type Ia supernovae showed that the universe's expansion was accelerating, driven by a mysterious force. This finding has profound implications for the cosmic web, as dark energy stretches its filaments and slows the growth of its structures. Gravitational lensing, a phenomenon predicted by Einstein's general relativity, has become a powerful tool for studying the cosmic web. By observing how light from distant galaxies is bent by intervening mass, astronomers can map the distribution of dark matter within the web. Surveys like the Dark Energy Survey, DES, and the upcoming Euclid mission have used gravitational lensing to create detailed maps of the web's invisible scaffolding. One of the most exciting recent milestones is the direct detection of the cosmic web's filaments through observations of the Lyman Alpha forest and X-ray emissions. The MUSE instrument on the Very Large Telescope and the eROSITA X-ray telescope have provided the first images of these elusive structures, revealing the filaments that connect galaxies and clusters across vast distances. Simulations have also played a crucial role in the journey to understand the cosmic web. Projects like the Millennium Simulation, Illustris, and Eagle have recreated the formation and evolution of the web in virtual universes. These simulations, based on the principles of dark matter, dark energy, and cosmic expansion, have matched observations with remarkable accuracy, validating our theories and providing new insights into the web's dynamics. Despite these milestones, the exploration of the cosmic web is far from complete. Future observatories, such as the Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope, and the Square Kilometre Array, SK, promise to unveil new details about the web's structure and evolution. These instruments will provide higher resolution maps, deeper surveys, and broader coverage of the electromagnetic spectrum, opening new windows into the web's mysteries. Reflecting on the history of cosmic web observations underscores the power of human curiosity and ingenuity. Each milestone represents a step forward in our quest to understand the universe, from the first telescopic surveys to the cutting-edge instruments of today. The cosmic web, once an abstract concept, has become a vivid and tangible reality, a testament to the progress of science and our capacity to explore the cosmos. Intersections of science and philosophy. The cosmic web, a vast and interconnected structure spanning the observable universe, is not only a subject of scientific inquiry, but also a profound source of philosophical reflection. Its intricate filaments and sprawling voids invite questions that transcend the boundaries of physics and astronomy, touching on the nature of existence, the origins of order, and humanity's place in the cosmos. How does the study of the cosmic web bridge the realms of science and philosophy, and what deeper insights does it offer? At its core, the cosmic web embodies the interplay between simplicity and complexity. From the nearly uniform state of the early universe, quantum fluctuations grew into the intricate patterns of the web, guided by the fundamental forces of nature. This transformation raises philosophical questions about the origins of structure. Why does the universe exhibit such ordered patterns, and what underlying principles govern its evolution? The concept of the cosmic web also resonates with philosophical ideas about interconnectedness. The web links galaxies, clusters, and filaments into a cohesive whole, illustrating that no part of the universe exists in isolation. This interconnectedness parallels ancient philosophical and spiritual traditions that view existence as a network of interdependent phenomena. The cosmic web, in this sense, becomes a modern scientific representation of a timeless idea. The role of dark matter and dark energy in shaping the cosmic web further deepens these reflections. These mysterious components, which together constitute about 95% of the universe, are essential to the web's formation and evolution. Yet, their nature remains largely unknown. This gap in understanding raises questions about the limits of human knowledge. How much of the universe can we truly comprehend, and what mysteries will forever elude us? The vastness of the cosmic web also inspires contemplation of humanity's place in the cosmos. Our galaxy, the Milky Way, is a single thread in this immense tapestry, a reminder of our smallness in the grand scheme of the universe. At the same time, our ability to observe, model, and understand the web speaks to the unique capacities of human consciousness. The study of the cosmic web invites a dual perspective: humility in the face of the universe's scale, and wonder at our ability to uncover its secrets. One of the most profound philosophical questions tied to the cosmic web is the role of chance and necessity in the universe's design. The web structure arises from initial conditions set during the Big Bang, shaped by random quantum fluctuations. Yet, its evolution is governed by deterministic physical laws, such as gravity and the expansion of space. This duality prompts questions about the nature of the universe. Is it a product of randomness, necessity, or some combination of both? And what does this imply about the existence of purpose or design in the cosmos? The idea of the cosmic web as a structure also challenges traditional notions of space and time. In modern cosmology, space itself is dynamic, expanding and interacting with the matter and energy it contains. The web, therefore, is not merely an arrangement of galaxies within space, but a feature of space-time itself. This perspective aligns with philosophical views that see space and time as relational rather than absolute, emphasizing their role in shaping the universe's fabric. The cosmic web also has implications for the philosophical debate about the anthropic principle, which considers why the universe's physical constants allow for the existence of life. The web structure, shaped by dark matter and dark energy, creates environments where galaxies, stars, and planets can form. These conditions, in turn, make life possible. Does the existence of the cosmic web suggest that the universe is fine-tuned for life? Or is it simply one of many possible configurations in a multiverse? Speculative ideas about the multiverse further intertwine science and philosophy. If our universe is just one of many, each with its own cosmic web, what does this mean for our understanding of reality? The concept of multiple universes challenges traditional notions of uniqueness and raises questions about the nature of existence itself. Are we part of an infinite ensemble of worlds? And if so, how does this alter our perception of significance and purpose? The study of the cosmic web also touches on existential questions about the future. As dark energy drives the universe's accelerated expansion, the filaments and nodes of the web will eventually drift apart, leaving isolated clusters of galaxies surrounded by vast voids. This scenario, known as the Big Freeze, paints a picture of a universe that becomes increasingly cold, dark, and empty over time. Such a fate invites reflection on the impermanence of structure and the ultimate destiny of all things. Beyond these cosmic scale questions, the cosmic web has cultural and symbolic significance. Its patterns echo structures found in nature, from neural networks in the brain to the filaments of mycelium in fungi. These parallels highlight the universality of certain patterns and suggest a deep connection between the microcosm and the macrocosm. The web becomes not just a scientific concept, but a metaphor for the interconnectedness of all things. Art, literature, and philosophy have long drawn inspiration from the cosmos, and the cosmic web is no exception. Its vastness and complexity have inspired works that explore themes of unity, transcendence, and the infinite. By providing a scientific framework for these ideas, the web bridges the gap between empirical observation and human imagination, enriching our understanding of both. In reflecting on the intersections of science and philosophy, the cosmic web reminds us that the quest for knowledge is not confined to the physical or the abstract. It is a journey that spans disciplines, connecting the measurable and the immeasurable, the tangible and the transcendent. The web's patterns, both observed and intuited, invite us to ponder the nature of reality, the origins of existence, and our role in the vast cosmic story. The web's future, predictions, and possibilities. The cosmic web, a sprawling network of filaments, nodes, and voids, has evolved over billions of years, shaped by gravity, dark matter, and dark energy. But what does the future hold for this grand structure? As the universe continues to expand and evolve, the web itself will undergo profound changes, reflecting the interplay of the fundamental forces that govern the cosmos. Exploring the future of the cosmic web reveals not only its potential transformations, but also the fate of the universe itself. The future of the cosmic web is tied to the accelerating expansion of the universe, driven by dark energy. This mysterious force, which constitutes approximately 68% of the universe's energy density, opposes gravity and causes the rate of expansion to increase over time. As a result, the filaments and nodes of the web are gradually being stretched and pulled apart. In the distant future, this expansion will profoundly alter the structure of the web. One of the most immediate consequences of dark energy is the isolation of galaxy clusters. While gravity binds galaxies together within clusters and filaments, the expansion of space increases the distances between these structures. Over time, galaxies that are not gravitationally bound will move beyond the observable horizon, effectively disappearing from view. This process will leave each galaxy cluster as an island universe, isolated within an ever-expanding void. As the universe expands, the filaments of the cosmic web will become more elongated and less dense. The inflow of gas and matter along these filaments, which fuel star formation in galaxies, will slow and eventually cease. This reduction in material flow will lead to a decline in star formation across the universe, as galaxies exhaust their remaining gas reserves. Without the replenishment provided by the web, galaxies will become quiescent, populated only by aging stars. The nodes of the cosmic web, regions where filaments intersect and galaxy clusters reside, will also change over time. Gravity will continue to pull matter inward within these dense regions, leading to the growth of superclusters and the formation of even larger structures. However, this growth will be limited by the influence of dark energy, which will slow the accretion of new material. Over billions of years, these nodes may evolve into massive, isolated structures surrounded by vast voids. The ultimate fate of the cosmic web depends on the nature of dark energy. If dark energy remains constant, as predicted by the cosmological constant model, the universe will continue expanding at an accelerating rate. This scenario, known as the Big Freeze, envisions a future in which the web structures are stretched to their limits, leaving a cold, dark, and nearly empty universe. In this state, stars will burn out, black holes will slowly evaporate, and the cosmic web will fade into obscurity. Alternative models of dark energy propose different outcomes for the cosmic web. If dark energy becomes stronger over time, the expansion of the universe could accelerate to such an extent that even the filaments and nodes of the web are torn apart. This scenario, known as the Big Rip, would result in the complete dissolution of all structures, from galaxies to atoms, as the fabric of space-time itself is stretched to infinity. Conversely, if dark energy weakens or reverses, gravity could regain dominance, leading to a contraction of the cosmic web. In this Big Crunch scenario, the universe's expansion would halt and reverse, causing the web's structures to collapse inward. This process would compress the filaments, nodes, and voids into a single, dense state, potentially setting the stage for a new cosmic cycle. Beyond these grand scenarios, the cosmic web's future also raises questions about the persistence of smaller structures within it. For example, galaxies within nodes may merge to form massive elliptical galaxies, while black holes at their centers continue to grow. These black holes could become the dominant remnants of the web, as their immense gravitational pull allows them to survive long after other structures have dissipated. The role of dark matter in the Webb's future is another area of interest. As dark energy dominates the universe, the influence of dark matter will diminish, altering the gravitational dynamics that shape the Webb. Over time, the distribution of dark matter within filaments and nodes may become increasingly diffuse, further contributing to the Webb's fragmentation. Observing the Webb's future evolution is, of course, a challenge limited by the timescales involved. However, simulations offer a powerful tool for exploring these possibilities. By modeling the behavior of dark matter, dark energy, and ordinary matter, simulations can predict how the cosmic web will change over billions or even trillions of years. These models provide a glimpse into the universe's distant future, offering insights into the fate of its largest structures. The future of the cosmic web also prompts philosophical reflections on the nature of time and existence. As the web evolves, its changing structures remind us of the impermanence of all things, from galaxies to the universe itself. The eventual dissolution of the web, whether through the Big Freeze, Big Rip, or another scenario, underscores the transient nature of even the grandest cosmic phenomena. Despite its eventual fate, the cosmic web's legacy will endure in the scientific and philosophical insights it has inspired. Its intricate patterns, shaped by the interplay of forces over billions of years, reflect the universe's capacity for complexity and order. The study of the web reminds us that the cosmos is not static, but a dynamic, evolving system, where even the largest structures are subject to change. Reflecting on the web's future invites us to consider our own place within this vast and evolving cosmos. As inhabitants of the Milky Way, a single thread in this immense tapestry, we are part of the web's story. By studying its past, present, and future, we not only uncover the mysteries of the universe, but also deepen our connection to it, finding meaning in its patterns and processes. Energy streams in the cosmic web. The cosmic web, with its sprawling filaments and intricate nodes, is not a static structure. It is alive with motion, shaped by the dynamic flows of matter and energy that traverse its vast network. These energy streams, rivers of gas, dark matter, and radiation, play a vital role in the formation and evolution of galaxies, clusters, and the web itself. By following these streams, we uncover the mechanisms that drive the universe's large-scale structure and sustain its ongoing transformation. At the heart of the cosmic web's energy streams lies the gravitational pull of dark matter. This invisible substance forms the backbone of the web, creating the dense regions that act as gravitational wells. These wells draw in ordinary matter, baryonic gas and dust, along the web's filaments, channeling it toward nodes where galaxy clusters reside. The gravitational energy of dark matter thus governs the flow of material within the web, orchestrating its growth and evolution. One of the most important processes associated with energy streams in the cosmic web is the accretion of gas. As gas flows along filaments, it feeds into galaxies and clusters, providing the raw material for star formation. This process sustains the growth of galaxies, allowing them to form new stars and develop complex structures like spiral arms. Without these streams, galaxies would quickly deplete their gas reservoirs, halting star formation and leaving them as barren collections of aging stars. These streams of gas are not uniform, but exhibit a range of temperatures, densities, and velocities. The coldest, densest gas flows directly into galaxies, where it collapses to form stars. Warmer gas, meanwhile, surrounds galaxies in halos, gradually cooling and accreting over time. This interplay between cold and warm gas creates a dynamic cycle of inflow and outflow that regulates star formation and galactic growth. Energy streams also fuel the growth of galaxy clusters, the largest gravitationally bound structures in the universe. Within clusters, the inflow of gas along filaments creates a hot, ionized medium known as the intercluster medium, ICM. This gas, heated to millions of degrees by gravitational compression, emits X-rays that reveal the structure and composition of the cluster. The energy streams feeding these clusters are responsible for their immense mass and luminous appearance. The interaction between energy streams and galactic environments can trigger spectacular phenomena. For example, As gas flows into galaxies, it can be shock-heated by the galaxy's gravitational potential, creating regions of intense radiation and star formation. Conversely, outflows of energy from galaxies, driven by supernovae or active galactic nuclei, AGN, can push back against the inflowing gas, shaping the distribution of material and influencing the galaxy's evolution. AGN, powered by supermassive black holes at the centers of galaxies, are particularly important sources of energy in the cosmic web. These black holes emit powerful jets and winds that can extend for hundreds of thousands of light years, influencing the flow of gas within filaments and clusters. AGN feedback not only regulates star formation within galaxies, but also redistributes energy throughout the surrounding medium, impacting the dynamics of the web. Dark energy, the mysterious force driving the accelerated expansion of the universe, also plays a role in shaping the web's energy streams. As the universe expands, dark energy stretches the filaments of the web, altering the flow of material within them. Over time, this expansion reduces the density of the streams, slowing the inflow of gas into galaxies and clusters. This process contributes to the gradual decline in star formation observed in the universe today. Observing energy streams within the cosmic web presents significant challenges due to their diffuse and faint nature. However, astronomers have developed innovative techniques to detect and study these flows. The Lyman alpha forest, a series of absorption lines in the spectra of distant quasars, reveals the distribution of hydrogen gas along the web's filaments. By analyzing these absorption patterns, scientists can trace the movement of gas within the web. X-ray observations, conducted by telescopes like Chandra and XMM Newton, provide another window into energy streams. These instruments detect the hot gas within clusters and filaments, revealing the flows of energy that sustain the web's largest structures. Radio telescopes, such as those in the Square Kilometre Array, SK, are also crucial for studying the energetic jets and winds produced by AGN. Simulations offer a complementary approach to understanding energy streams. Projects like Illustris and Eagle model the flow of gas, dark matter, and radiation within the cosmic web, providing detailed visualizations of its dynamics. These simulations reveal how energy streams interact with galaxies, clusters, and filaments, offering insights into processes that are difficult to observe directly. One of the most intriguing aspects of energy streams is their role in shaping the web's overall structure. The flow of matter along filaments determines the size and density of nodes, while feedback from galaxies and clusters influences the distribution of material within the web. These processes create a dynamic equilibrium, where inflows and outflows balance each other to maintain the web's intricate patterns. Energy streams also highlight the interconnected nature of the cosmic web. The material flowing into a galaxy today may have originated in a distant part of the web, carried along filaments over billions of years. This interconnectedness underscores the unity of the universe's structure, where every component is linked by the flows of energy and matter that traverse the web. The future of research on energy streams will be driven by advances in observational technology and simulation techniques. Next-generation instruments like the Athena X-ray Observatory and the Vera C. Rubin Observatory will provide higher-resolution views of the web's dynamics, revealing new details about its energy flows. Combined with increasingly sophisticated simulations, these observations will deepen our understanding of the processes that sustain the cosmic web. Reflecting on the energy streams of the cosmic web offers a glimpse into the dynamic forces that shape the universe. These streams, flowing across billions of light years, connect galaxies, clusters, and filaments into a single, evolving system. By following these flows, we uncover the mechanisms that drive the web's formation and transformation, illuminating the intricate dance of energy and matter that defines the cosmos. The cosmic web and the fate of star formation. The cosmic web, a vast network of filaments connecting galaxies and clusters, is the stage upon which the universe's stars are born. Star formation, the process of converting gas into luminous stellar objects, depends on the dynamic flows of material within the web. Yet, as the universe evolves, the conditions for star formation are changing. By examining the relationship between the cosmic web and star formation, we can explore the future of the universe's light and the eventual fate of its stars. Star formation begins in the dense regions of the cosmic web, where gas collects within galaxies and filaments. The gravitational pull of dark matter draws baryonic matter, hydrogen and helium gas, into these regions, creating reservoirs of material for star formation. As gas cools and condenses, it forms molecular clouds, the nurseries of stars. These clouds collapse under their own gravity, igniting nuclear fusion and giving birth to stars. The inflow of gas along filaments is crucial for sustaining star formation in galaxies. Without these energy streams, galaxies would quickly exhaust their gas supplies, halting the formation of new stars. This inflow is most efficient in the dense environments of filaments and nodes, where the gravitational pull is strongest. However, as the universe expands and the cosmic web evolves, the availability of gas for star formation is decreasing. One of the primary drivers of this decline is the cosmic gas supply problem. Over billions of years, much of the gas in the universe has been incorporated into stars, galaxies, and clusters. The remaining gas is either too diffuse or too hot to condense into stars. In addition, feedback processes, such as supernova explosions and active galactic nuclei, AGN, eject gas from galaxies into the intergalactic medium, IGM, further reducing the available material for star formation. Dark energy, the mysterious force driving the accelerated expansion of the universe, also contributes to the decline in star formation. As dark energy stretches the filaments of the cosmic web, it reduces the density of gas within them, slowing the inflow of material into galaxies. This process, combined with the depletion of gas reserves, is leading to a gradual decline in the universe's star formation rate, a trend that began several billion years ago and is expected to continue. The cosmic web also influences the spatial distribution of star formation. In dense regions, such as galaxy clusters, interactions between galaxies and the surrounding environment can quench star formation. Processes like ram pressure stripping, where a galaxy's gas is removed by its motion through the hot intercluster medium, leave galaxies unable to form new stars. Similarly, gravitational interactions and mergers in these regions can disrupt galactic structures, altering star formation rates. In contrast, galaxies located along filaments or in less dense environments may experience more favorable conditions for star formation. These galaxies can draw gas from the IGM without significant interference, maintaining higher star formation rates. The cosmic web thus creates a gradient of star formation activity, with more vigorous star formation occurring in filaments and quieter galaxies dominating clusters. Observations of star formation across the cosmic web provide a window into the universe's history and its eventual fate. Surveys like the Hubble Space Telescope's Cosmos Field and the ALMA telescope have mapped star formation in galaxies across different environments, revealing how the cosmic web shapes their evolution. These studies show that the peak of star formation occurred about 10 billion years ago, during an era known as cosmic noon, when gas was more abundant and galaxies were more active. Simulations of the cosmic web, such as Illustrious TNG and Eagle, have also provided valuable insights into the future of star formation. These models predict that as the universe continues to expand, the rate of star formation will decline further. By the time the universe is 100 billion years old, star formation will have virtually ceased, leaving a universe populated by aging stars and the remnants of stellar evolution, such as white dwarfs, neutron stars, and black holes. The eventual cessation of star formation has profound implications for the cosmic web. Without the formation of new stars, the web's filaments and nodes will become dimmer and less active, transforming into a network of dark matter and dead galaxies. The luminous structures that define the web today will fade, leaving behind only the faint glow of cooling remnants. This decline also raises questions about the fate of existing stars and their role in the web's evolution. As stars age, they undergo processes that enrich their surroundings with heavy elements, contributing to the chemical evolution of the web. These elements, forged in the cores of stars, are the building blocks of planets, life, and future cosmic structures. Even as star formation wanes, the legacy of stars will persist in the form of enriched filaments and clusters. Despite the challenges posed by the decline in star formation, The study of the cosmic web offers a unique perspective on the universe's resilience and adaptability. The web's structures, shaped by the interplay of gravity, dark matter, and baryonic processes, reflect the dynamic nature of the cosmos. By understanding how these processes interact to sustain or inhibit star formation, we gain insights into the delicate balance that governs the universe. Future observations and simulations will continue to refine our understanding of the relationship between the cosmic web and star formation. Instruments like the James Webb Space Telescope, JWST, and the Nancy Grace Roman Space Telescope will probe the faintest and most distant regions of the web, uncovering the remnants of star formation and the conditions that shaped it. These discoveries will deepen our knowledge of the web's past and illuminate its future trajectory. The cosmic web and the fate of star formation are deeply intertwined, offering a narrative of growth, decline, and transformation. As the universe evolves, the interplay between the web's structures and the stars within them will continue to shape its story. By exploring this relationship, we not only uncover the mechanisms that drive cosmic evolution, but also gain a deeper appreciation for the fleeting brilliance of stars and the enduring patterns of the web. Cosmic voids, the universe's silent giants. While much attention is given to the dense filaments and luminous nodes of the cosmic web, the vast cosmic voids, the nearly empty regions between these structures, are equally significant. These silent giants, spanning tens to hundreds of millions of light years, represent the universe's most barren environments. Yet, their emptiness holds valuable clues about the nature of the cosmos, the forces shaping the cosmic web, and even the mysterious components like dark matter and dark energy. What role do voids play in the cosmic web, and how do they help us understand the universe's grand design? Cosmic voids are not entirely empty, but are characterized by extremely low densities of matter. They contain only about 10% of the average matter density of the universe, with a sparse population of galaxies scattered throughout. These galaxies, often referred to as void galaxies, are isolated and evolve under conditions very different from those in denser regions. Their properties provide a unique perspective on how environment influences galaxy formation and evolution. The formation of voids is a natural consequence of the universe's large-scale structure. After the Big Bang, tiny fluctuations in density seeded the growth of the cosmic web, while regions of higher density accumulated matter under the influence of gravity. Less dense regions lost material to their surroundings, becoming increasingly empty. Over billions of years, this process carved out the vast voids we observe today, bordered by the filaments and nodes of the web. The shapes of voids are often spherical or elliptical, reflecting their uniform expansion. Unlike the more chaotic environments of filaments and clusters, voids expand relatively uniformly due to the absence of significant gravitational forces. This uniformity makes voids excellent laboratories for studying the effects of dark energy, which accelerates the universe's expansion. By measuring the size and growth rate of voids over time, scientists can test models of dark energy and refine our understanding of its properties. Void galaxies, though few in number, are particularly intriguing. They tend to be smaller, less massive, and less luminous than their counterparts in denser regions. These galaxies often have irregular shapes and exhibit slower rates of star formation. The isolation of void galaxies means they experience fewer gravitational interactions, such as mergers or tidal forces, allowing them to evolve more passively. This lack of disturbance provides a window into galaxy formation in its simplest form, free from the complications of dense environments. The intergalactic medium, IGM, within voids also differs from that in filaments and clusters. The gas in voids is cooler and less ionized, reflecting the low density and lack of gravitational compression. Studying the IGM in voids can reveal details about the universe's early chemical enrichment, as these regions retain a more pristine composition compared to denser areas, which have been heavily influenced by supernovae and galactic winds. Cosmic voids also serve as a backdrop for studying the behavior of dark matter and dark energy. The gravitational effects of dark matter are weaker in voids, making them ideal for testing alternative theories of gravity or modifications to general relativity. Similarly, the influence of dark energy, which dominates the universe's expansion, is more apparent in these low-density regions. Observing how voids grow and evolve over time provides critical data for understanding these fundamental components of the universe. Gravitational lensing, a phenomenon where light from distant objects is bent by intervening mass, offers a powerful method for studying voids. By analyzing the weak lensing effects caused by the sparse dark matter within voids, scientists can map their mass distribution and compare it with predictions from cosmological models. These studies help refine our understanding of the relationship between dark matter, dark energy, and the large-scale structure of the universe. The alignment of voids with the cosmic web reveals their role as complementary components of the universe's structure. While filaments and nodes represent regions of high density and activity, voids provide the empty spaces that define the web's contrast and shape. Together, these elements create the intricate patterns observed in galaxy surveys and simulations. Voids are also useful for calibrating observational techniques and simulations. Their simplicity makes them ideal benchmarks for testing cosmological models and comparing theoretical predictions with real-world data. For instance, the distribution and sizes of voids are sensitive to the universe's overall matter density and the properties of dark energy. By studying voids, scientists can place constraints on these parameters and refine their models of cosmic evolution. Despite their importance, voids remain one of the least explored aspects of the cosmic web. Their faintness and lack of luminous structures make them challenging to observe, requiring advanced instruments and techniques. However, recent surveys like the Dark Energy Survey (DES) and the Sloan Digital Sky Survey (SDSS) have begun to map voids in unprecedented detail, providing new insights into their properties and distribution. The future of void research holds great promise, with upcoming missions like the Euclid Space Telescope and the Vera C. Rubin Observatory expected to revolutionize our understanding of these enigmatic regions. These instruments will provide deeper and more detailed surveys of voids, uncovering their role in shaping the universe and their connection to dark matter and dark energy. Cosmic voids, though often overlooked, are essential to the cosmic web's structure and evolution. Their vast emptiness highlights the delicate balance of forces that sculpt the universe, from gravity and dark matter to the relentless push of dark energy. By studying voids, we gain not only a deeper understanding of the universe's large-scale structure, but also new perspectives on its origins, dynamics, and ultimate fate. The cosmic web as a cosmic map. The cosmic web, with its sprawling filaments, dense nodes, and vast voids, serves not only as a structure within the universe but also as a map, a guide to understanding the cosmos' fundamental nature. By studying the web's patterns and connections, scientists can uncover insights about the distribution of matter, the behavior of dark energy, and the universe's history. In many ways, the cosmic web is the universe's blueprint, offering clues about its origins, evolution, and future. The cosmic web's role as a cosmic map begins with its ability to trace the distribution of dark matter, the invisible substance that makes up approximately 27% of the universe's total mass energy. Dark matter does not emit, absorb, or reflect light, making it undetectable through direct observation. However, its gravitational effects sculpt the cosmic web, influencing the distribution of galaxies and gas. By mapping the web, astronomers can infer the underlying dark matter framework that binds the universe together. One of the most powerful tools for mapping the cosmic web is gravitational lensing. When light from a distant galaxy or quasar passes through a massive foreground structure, such as a galaxy cluster, it is bent by the gravitational field of the intervening matter. This effect, predicted by Einstein's theory of general relativity, creates distortions in the observed images of background objects. By analyzing these distortions, scientists can construct detailed maps of the dark matter distribution, revealing the web's structure. The study of large-scale galaxy surveys has also been instrumental in mapping the cosmic web. Projects like the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey (DES) have cataloged the positions of millions of galaxies, creating three-dimensional maps that trace the web's filaments and nodes. These surveys provide a vivid picture of the universe's large-scale structure, showcasing how galaxies are clustered along the web's intricate network. The cosmic web also serves as a map of the early universe, linking present-day structures to their origins in the Big Bang. The cosmic microwave background (CMB), the faint afterglow of the Big Bang, carries the imprint of the initial density fluctuations that gave rise to the Webb. Observations of the CMB, conducted by missions like Planck and WMAP, reveal the seeds of the Webb's filaments and voids, providing a snapshot of the universe's infancy. Simulations of the cosmic web, such as the Millennium Simulation and Illustris TNG, have further advanced our ability to map its structure. These models start with the initial conditions observed in the CMB and use the laws of physics to simulate the universe's evolution over billions of years. By comparing these simulations with observations, scientists can refine their understanding of the processes that shape the Webb and test theories about dark matter, dark energy, and cosmic expansion. The cosmic web is also a map of cosmic flows, the movements of galaxies and matter within the universe. These flows are driven by gravitational interactions, with galaxies moving along filaments toward denser regions, such as galaxy clusters. By studying these motions, astronomers can infer the distribution of mass in the universe and identify features like the Great Attractor, a massive gravitational anomaly pulling galaxies in our local region of the Webb. The Webb structure provides a map of cosmic evolution, showing how the universe's components have changed over time. The density and arrangement of filaments and voids reflect the interplay between gravity and dark energy, revealing the mechanisms driving the universe's expansion. By studying the Webb's growth, scientists can test models of dark energy and explore how its influence has evolved over billions of years. One of the most exciting aspects of the cosmic web as a map is its potential to uncover new physics. For example, discrepancies between observed structures and theoretical predictions could point to unknown phenomena, such as modifications to general relativity or the existence of exotic particles. The Webb's patterns and behaviors serve as a testing ground for these ideas, offering a bridge between cosmology and fundamental physics. The cosmic web also offers a framework for understanding the chemical evolution of the universe. As gas flows along filaments into galaxies, it carries the raw materials for star formation and chemical enrichment. The distribution of elements like hydrogen, helium, and heavier metals within the web reflects the history of stellar processes and supernovae, providing a record of the universe's transformation from simplicity to complexity. The cosmic web's mapping capabilities extend to the search for habitable environments. By tracing the distribution of galaxies and their properties, the web can help identify regions where conditions are most favorable for the development of life. For instance, galaxies in less dense regions of the web may experience fewer disruptive interactions, creating stable environments for planetary systems to evolve. Despite its value as a cosmic map, the web remains only partially charted. Many of its features, such as the detailed distribution of dark matter and the properties of intergalactic gas, are still being explored. Upcoming missions, like the Vera C. Rubin Observatory, the Euclid mission, and the Nancy Grace Roman Space Telescope, promise to provide more comprehensive and detailed maps, revealing new facets of the web structure. The cosmic web, as a map, is not just a tool for understanding the universe. It is also a source of inspiration. Its intricate patterns, shaped by the interplay of fundamental forces, remind us of the universe's underlying unity and complexity. By studying the web, we not only uncover the secrets of the cosmos, but also deepen our appreciation for the interconnectedness of all things. Reflecting on the cosmic web as a map invites us to consider how much of the universe we have yet to explore. Each filament, void, and node represents a chapter in the story of the cosmos, a narrative written across billions of years and billions of light years. By charting this grand structure, we connect ourselves to the vast, evolving tapestry of the universe, finding our place within its intricate design. The role of supermassive black holes in the cosmic web. Supermassive black holes, the enigmatic giants at the centers of most galaxies, are key players in the dynamics of the cosmic web. These massive objects, with masses millions to billions of times that of the Sun, influence their host galaxies, surrounding clusters, and even the larger structures of the web itself. Their immense gravitational pull, energetic outflows, and complex interactions with surrounding matter link them intrinsically to the evolution of the cosmic web. What roles do these titans play? And how do they shape the structure and development of the universe? Supermassive black holes, SMBHs, are typically found at the centers of galaxies, particularly in dense regions of the cosmic web, such as nodes and filaments. These locations, where galaxies cluster and interact, create ideal conditions for the growth of SMBHs. Over time, SMBHs accumulate mass by accreting gas and stars and merging with other black holes during galactic collisions. The most dramatic activity of SMBHs occurs during their active phases, when they accrete large amounts of matter. This accretion generates enormous energy, often outshining the combined luminosity of the entire host galaxy. These energetic objects, known as active galactic nuclei, AGN, or quasars, emit radiation across the electromagnetic spectrum, from X-rays to radio waves. This activity is not confined to the galactic center. It extends outward, influencing the surrounding cosmic web. One of the most significant ways SMBHs impact the cosmic web is through feedback mechanisms. The powerful jets and winds generated by AGN can inject energy into the intergalactic medium, IGM, heating the surrounding gas and altering its behavior. This process, known as AGN feedback, regulates the flow of gas into galaxies, suppressing star formation and preventing excessive cooling of the IGM. In doing so, SMBHs help maintain the balance of matter and energy within the web. AGN feedback also contributes to the enrichment of the IGM with heavy elements. The energetic outflows from SMBHs carry metals, elements heavier than hydrogen and helium, produced in stars and supernovae into the surrounding medium. This enrichment process spreads the building blocks of planets and life across the cosmic web, linking SMBHs to the chemical evolution of the universe. The influence of SMBHs extends to the largest structures in the cosmic web, such as galaxy clusters. In these dense environments, SMBHs play a role in shaping the intracluster medium, ICM, the hot, ionized gas that fills the spaces between galaxies. Jets from SMBHs in central cluster galaxies can create cavities or bubbles in the ICM, redistributing energy and preventing the gas from cooling and forming stars. This process, observed in clusters like the Perseus cluster, demonstrates the far-reaching effects of SMBHs on their surroundings. The growth and activity of SMBHs are closely tied to the dynamics of the cosmic web. For instance, SMBH mergers, which occur during galactic collisions, are more frequent in dense regions of the web where interactions between galaxies are common. These mergers not only increase the mass of SMBHs, but also release gravitational waves, ripples in space-time that propagate across the web. Observations of these waves, made possible by instruments like LIGO and Virgo, provide a new way to study the interactions between SMBHs and the web. The relationship between SMBHs and the cosmic web is also evident in their spatial distribution. Observations show that quasars and AGN are more likely to be found in regions of high galaxy density, such as filaments and nodes. This correlation reflects the influence of the web structure on the availability of gas for accretion and the frequency of galaxy interactions. Despite their significance, many aspects of SMBHs remain mysterious. For example, how do SMBHs grow so rapidly in the early universe, reaching masses of billions of suns within a few 100 million years after the Big Bang? The connection between SMBH growth and the cosmic web may hold the key, as dense filaments provide a steady flow of gas to fuel their accretion. The study of SMBHs is advancing rapidly, thanks to cutting-edge observational tools and simulations. Telescopes like the Event Horizon Telescope, EHT, have captured the first images of SMBHs, revealing the shadows cast by their event horizons. Meanwhile, missions like the James Webb Space Telescope, JWST, and the Euclid mission are exploring the role of SMBHs in the evolution of galaxies and the web. Simulations such as Illustris TNG model the interactions between SMBHs, galaxies, and the cosmic web, offering insights into their complex relationships. SMBHs are not just local phenomena. They are integral to the cosmic web's evolution. By regulating the flow of gas, shaping the distribution of matter, and enriching the IGM, These massive objects influence the web on multiple scales. Their activity connects the small-scale processes of galaxy formation with the large-scale structure of the universe, highlighting the interconnectedness of the cosmos. Reflecting on the role of SMBHs in the cosmic web invites us to consider the universe's capacity for transformation and connection. These enigmatic giants, hidden at the hearts of galaxies, exert a profound influence on the structures that define the cosmos. By studying them, we uncover not only the mechanisms that shape the web, but also the forces that drive the universe's evolution. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.